Alright, hello everyone. So you would have just enjoyed the awkward 30-second silence when I've just started streaming, but I'm waiting to see that it's appeared on YouTube. If you've ever wondered why that always happens at the beginning of every seminar, that's why. It's just because of the 30-second delay between what's happening over here and what you're seeing on YouTube. So yeah. But in any case, welcome to our Math2601 seminar, part 2. Jerry and Steve went over the first half of the course yesterday. And they covered a lot of ground regarding the first part of the course. But today I'm Bruce, and my colleague Jay will be talking about the second half of the course, which is on these 4 topics. So I'll be covering the first 2, determinants and eigenvalues and eigenvectors, and Jay will be covering the second half, which is on canonical Jordan forms and matrix exponentials. And you'll find that this first half of the course, it really just builds quite a lot on what you did in first year. So there'll be a lot of exciting stuff ahead, but the second half, it would be basically completely new and stuff that you wouldn't have seen in first year before. So without further ado, we'll start with some determinant stuff. Okay, so before we actually talk about determinants though, we have to talk about permutations. This is something that's covered more extensively in Math2601, but it's useful because it occasionally turns up in exams. But what is a permutation? Well, we've been doing them for a long time. Basically, it's a reordering of a set of n items. So, well, for example, you have like items, 4 items, you like swap the first 2 or something, or you like swap the second and third. But we want a formal way of writing it out. So what we say is that we do it in matrix form. And the first row of your matrix form is always just going to be the elements in order. So 1, 2, 3, 4, 5, 6, and so on. And what this second row basically means is you can read it like this. This item, so number 2, gets sent to the position at the bottom, right? So for example, the second item is sent to the 4th position, right? And 1 stays the same, the first item stays the same. The third item moves to the 2nd position, and the 4th item moves to the 3rd position. So that's just a nice way of writing out a permutation. Maybe just another example, something like this. 1, 2, 3, 1, 3, 2. So in this permutation, we've got 3 objects. The first object stays the same place, but the second object moves to the 3rd position, and the third object moves to the 2nd position. So basically what's happening is we're swapping items number 2 and item number 3, right? So that's just a nice way of writing permutations. Yeah, so that's our introduction. We can also write this as a function, so a permutation can be seen as a function, and we often use the Greek letter sigma. So sigma 1 equals 1 means that, well, basically this item at the top gets mapped to the bottom one. So sigma 1 equals 1 means that 1 goes to the 1st position. So same kind of idea as what we had before with the matrices. 1 is sent to 1. Over here, 2 is sent to 4. 3 is sent to the 2nd position, and 4 is sent to the 3rd position. So you can just read it out like this. Sigma of any number at the top is basically just the number that's below n in this matrix. Cool. So that's just some stuff we need to write permutations out. But the stuff we need for determinants is essentially the sign of a permutation. And what is the sign of a permutation? To revise this, it's an indication of something called inversions. So what is an inversion? Inversion is kind of what the name suggests. So you have 2 items. Maybe let's just take 1 and 2. And initially they're in a certain order. So 1 comes first, then we have 2, then we have 3, and so on. But what an inversion is basically in the permutation, let's just say we have the matrix 2, 1, 3, 4. Hopefully by now we understand that this matrix would just be the permutation that swaps 1 and 2. There's actually an inversion here because 1 is before 2. So we write 1 is less than 2. But sigma 1 is actually equal to 2. Whereas sigma 2 is equal to 1. So they've actually been swapped. The order's been swapped. So essentially that's what this condition means. It says pairs x, y, with x is less than y, and sigma x is greater than sigma y. So essentially, initially x was before y in the permutation, but then eventually once you permuted them, they swapped around. And, well, what is the sign of it? Well, the sign tells us whether there's an even number of inversions. So the sign of 1 is equal to, a sign of a permutation is equal to 1 if it's even. But otherwise, if it's odd, if the number of inversions is odd, then sine is equal to -1. So basically all you have to do is just count the inversions. Even means you have 1. Odd means you have -1. Okay, so an example is over here. So the sign of the permutation corresponding to 1, 2, 3, 4, 5, 1, 3, 2, 4, 5. It's an easy example because most of the numbers stay in the same place. 1 stays in the same place, 4, 5, and so on. The only really objects that have swapped positions are 2 and 3. So in other words, that's just one inversion. And because there's just one inversion, it's going to be, you can probably guess it's going to be odd. So the answer to this is -1. Cool. Alrighty. So some properties of the sign which you might look into. The sign of the composition of two transformations. So if you do one permutation after the other, then the sign of that resultant permutation is equal to the product of the individual signs. The second one is really important, and it's the most important thing we actually need for determinants. The sign of a transposition is equal to -1. And what is that? Whenever you swap two elements, that's a transposition. That means any permutation that swaps two elements is odd. And this last one is that every permutation can be expressed as a composition of transpositions. You won't need to know this too much for this course. This is more for higher level algebra courses. But basically, the sign of a permutation is equal to -1 to the power of k, where k is the number of transpositions you need for that permutation. And why is that? Because if you've got a permutation, and you express it as a composition of transpositions, and you have k transpositions, then from this property over here, number 1, the sign of sigma is just equal to the product of the individual ones. And that means that because every transposition, when you're swapping two things, has a sign of -1, you get -1 times -1, all the way down to -1. So that just gives you -1 to the power of k. Right, so just a useful fact for this course, but basically you can express a permutation in terms of transpositions and work out the sign via that method. So that's our first kind of look into permutations. Okay, we'll look at determinants now. And this is just a property that you would have known from first year. So the determinant of a matrix can be expressed in this form. So the sum from 1 to p of this thing. And basically what this is you really go through, I won't go through this too much because it doesn't come up that much. Basically, let's say we have a 3 by 3 matrix. And the determinant of a 3 by 3 matrix is a bit hard to calculate. So what you want to do is you want to go through the individual terms, Aij. Right, so you go through the individual terms, 1, 2, 3, and you choose any row that you want to do this with. And what you do is you say, for each of these elements, so let's just say element 1, you compute what's called the Aij minor. So what you do is you remove the column and the row that correspond to this number. So pick 1, you remove the column and the row that correspond to this number. So in this case, it would be the first row and the first column, right? And then you look at this matrix over here, and that's called the minor corresponding to this element, right? So 1 corresponds to this black box over here. And just as another example, this element over here, 2, would correspond to the matrix with this column and this row removed. So it would correspond to the matrix 4, 6, 7, 9. Okay? And so if this, for example, is the 1, 1 element, which it is, then the matrix you get from removing the first row and the first column is called the 1, 1 minor. So this circle and this square, this is the 1, 1 element, and this is the 1, 1 minor. And why do we care about that? Well, basically what we're doing when we're computing determinants I'll just redraw this. Is we're going through all the elements in any individual row, and we're taking the alternating sum. So this corresponds again to this minor down here. So 1 corresponds to 5, 6, 8, 9. And what you do is you take 1 and you multiply by the determinant of 5, 6, 8, 9, which you should know from first year to just be 5 times 9 minus 6 times 8. Right? And that's our first element of the determinant. And what you do is you go through the row like this, and the next one will be 2, and then you have 4, 6, 7, 9, and then you subtract that one. So minus 2 times determinant of 4, 7, 6, 9. Then you go to the last one. Basically, you go all through the row, and then you add 3 times, you guessed it, the determinant of 4, 5, 7, 8. Right, and so once you've done that, you get the determinant of the entire matrix. And really, the only situation where you'll be using this very much is just to calculate 3 by 3 matrices. So this really is sufficient as an example. Really, all you have to do is just go through one row or one column and just take this alternating sum. Right, so take the element. This is Aij. And you multiply by a det of Aij, and that's really what I talked about just then, the Ij minor. So from removing the ith row and the jth column. Won't go into that too much because that's from first year, but that's just an introduction to determinants. Right, these are the important theorems we need to know. So number 1, the determinant of an upper triangular matrix or a lower triangular matrix is just the product of the diagonal terms. So realistically, if we have something like this, you don't have to do all that rigmarole of like going through the minors and all that nonsense. You just really just take the diagonal terms and multiply them through. So the determinant of this would just be 1 times 2 times 3, which equals 6. The second one is quite important too. So if you take the transpose of a matrix, it doesn't change the determinant. And it's just because this kind of formula, well, basically it works for either rows or columns, right? So it doesn't matter whether everything is a row or a column. If you switch around the rows versus the columns, you get the same determinant. So the determinant of A is equal to the determinant of its transpose. The third one over here, if you recall this notation, I'll just remind you from last time. This is the adjoint of A, which is equal to the conjugate transpose of A. And it kind of makes sense that if you take the conjugate transpose, well, we already know that the transpose does nothing to the determinant. So really all we're doing is just taking the conjugate of every term. So it makes sense that if you get the adjoint of a matrix, the determinant is conjugated to. These are some properties that also you would have learnt from first year, but now we're kind of formalizing them a bit more. So if a permutation is applied to the rows of A, as we recall, the determinant is multiplied by the sign of the permutation. So let's just say we swap 2 rows, for example. Right, I take this and I say, let's just swap rows 1 and 2. I've swapped them. That's a transposition, right? Transposition has sign 1. Sorry, sign -1. So in other words, to get from here to there, my determinant is multiplied by -1. Right, so that's a special case of rule number 4. Number 5, if any row of A has a multiple of another row added to it, the determinant is unchanged. That's from first year. We've learnt about that before, because this is one of the key tenets of row reduction. The idea is that if we reduce a matrix using standard row reduction, and we just add multiples of one row to another, then the determinant shouldn't be changed, right? Which means we can basically try to reduce, if we recall from first year, reduce any matrix down to its row echelon form, and try to get an upper triangular matrix. This is just an example, it doesn't actually reduce to that. But if we try to get this upper triangular matrix, we can then just say the determinant is the product of these 3 things. Okay, so this is just formalizing what we did in first year. And number 6, if a row of A is multiplied by a constant, then the determinant is also multiplied by that constant. So don't think, for example, that if you just take any matrix and you multiply the entire thing. So you multiply the entire thing by a constant. Don't think that this actually implies that the determinant will be multiplied by 2, right? Because actually what you have to do is apply it row by row, right? So if you do actually multiply all 3 rows by 2, then the determinant is actually multiplied by 2, but not just by 2, it's multiplied by 2 3 times. So it's multiplied by 8. Right, so just apply the multiples row-wise or column-wise, and the determinant will follow that rule as well. And lastly over here, any matrix with a 0 row or a 0 column has a 0 determinant. So if you recall from first year, if you ended up with any matrix with an incomplete row echelon form, so it has a 0 row, then you would have deduced that its determinant is equal to 0. And that's just formalizing what we did in first year. So let's do an example, and realistically, this technically is very similar to what you did in first year. It's just a bit more conceptually difficult because you have like variables here as well instead of just numbers. So basically what they're getting us to do is just take this matrix and explain why its determinant is equal to a plus b plus c times the determinant of another matrix. So you can guess that we're going to be using those properties, those rules about transforming rows and columns that we just learnt about. So let's just think about what we're trying to do. We're trying to somehow go from this matrix and apply transformations to get to this matrix. Because we want to basically say determinant of A, if we can apply transformation to this and reduce it to B, then we'll end up with a relation linking the determinant of A with the determinant of B. So let's take this. And let's see how we can try to reduce it to this thing. Okay, so somehow we need to basically change this row to a row of 1s. Right, and that basically means we have to make all of these elements in the first row the same. Right, so how can we possibly do that? Well, for example, let's just try, because we also have this over here. We want to show that the determinant of A is equal to a plus b plus c times the determinant of the second matrix. So clearly you can sense that there's going to be some a plus b plus c in the second matrix that we're going to be taking out of the matrix eventually. So how can we get this to show a plus b plus c? Well, one example is this is a minus b minus c. If we want to get an a plus b plus c, then maybe we can add these two terms to it. But we can't just add 2 terms to this element at the top just without doing anything. Realistically, what we have to do is add the second row and the third column. So essentially what I'm saying is we want to be adding the second row and the second column in order to get some a plus b plus c term. Because then all of this will cancel out if you add these 3 together, and you'll get a plus b plus c. So let's try doing that. And in fact, what we get is, well, first of all, we'll add the second row to it. So we'll add 2b first. And we end up with this. Basically, if I can write this out in our reduced row echelon form, row 1 becomes row 1 plus row 2. Then you can guess what we're going to do next. We're going to do row 1 and say, make that row 1 plus row 3. Right, and that's what we do next. And we end up with this. So you can do it by yourself, but basically you get a minus b minus c plus 2b plus 2c over there. Then this one turns into 2a plus b minus c minus a plus 2c. And then this one becomes 2a plus 2b plus c minus b minus a. And all of those just become a plus b plus c. And hopefully you can get what we're getting at right now. We're going to be trying to change this to 1. So we use that lovely property that if you take out any element, if you multiply any row by a constant, then the determinant is multiplied by that constant. So essentially that means you can take out factors from rows. So if this row has a common factor, you can basically take it out and replace it with, and basically divide over here. Cool, and we're looking pretty good, because that's exactly what they wanted us to show. Cool. Alrighty, the next part of the question is getting us to show that the determinant of b, in fact, is equal to this thing over here. So in other words, they want us to show that these things have the same determinant. Again, it's going to be a matter of transformations. Okay, so we want to get this 1 and somehow turn it into 0. So clearly there's going to be some kind of subtraction involved. But in this case, it won't be subtraction of rows because you can't really subtract anything in this row that would turn it into a 0. It's going to be a subtraction of columns. So specifically, you can probably guess that this row, this column, sorry, you're going to subtract one of these columns. Right, so what we'll do in this case is perhaps we'll subtract this first column. Right, and you can really do trial and error. Maybe you can try column 2 becomes column 2 minus column 1, or column 2 becomes column 2 minus column 3. And both of those would result in a 0 term over here because you've got 1 minus 1. But in this case, we'll just do column 2 becomes column 2 minus column 1. And that's the first one over here. So yes, we get what we wanted. We get a 0 over here, and we get the right term over here as well. So comparing this with the final answer that we want, the first row is correct, the second row is correct, it's just the third row that we still need to change. And you can kind of sense what's going to happen here. We've got a 1 and a 2b over here. We want to somehow change that to a 0 and a 0. So where can we find a 1 and a 2b that we can subtract from this? Well, it's over here, right? You can replace column 3 with column 3 minus column 1. And that gives us this last thing over here. And then we're done, because that's what they wanted us to show. Cool. And the final thing they want us to do is find the determinant of b, and therefore give a factored form of determinant of a. Well, let's look at what we've shown so far. Determinant of b is equal to the determinant of this lovely little thing. And why is it lovely? Well, it's lovely because it's a lower triangular matrix. It's a lower triangular matrix, which means that basically we can just take the diagonal terms. So determinant of b is equal to, well, I'll just write this down. These two things multiplied, which is a plus b plus c squared. And then determinant of a, well, that goes back to the beginning of the question, right? Because we found this relation between a and b. Determinant of a is equal to a plus b plus c times that determinant. So coming back down, we just get a plus b plus c cubed. Cool, and that's our the end of this question. Cool, so hopefully that was a nice revision into determinants. It's a bit of a quick section because now we'll go into eigenvalues and eigenvectors, which are a bit more complicated. But yeah, let's just get right into it. Cool. So basically we're looking at a vector space and a linear transformation on that vector space. And if lambda is a scalar, so just a number, and v is just a non-zero vector, then you've seen this from first year. If we apply t to this vector, and we get a multiple of the original vector, so lambda v, then this is called an eigenvector, and this is called an eigenvalue. And just some notation you might not have seen in first year, spectrum. So the set of eigenvalues of t is called the spectrum, right? So all these values that satisfy this equation, they are called the spectrum of t. This is a useful concept, and we'll see why it's useful for eigenvectors. So a subspace U of V is said to be t invariant if t of u is a subset of u. And what that means is basically if you apply t to any vector in u, then that's also going to be inside u. So in other words, if you just take all the vectors in this vector space or this subspace and you apply the transformation to it, you don't get any new vectors, right? And that's what T invariance means. Because it's invariant under T, you don't get anything new under T. Cool, and so when we talk about eigenvectors, then recall again that we have these eigenvalues, and a new definition is called the eigenspace. The eigenspace corresponding to lambda, and we write it as E of lambda. So if, for example, 2 is an eigenvalue, then E2 of this transformation is equal to the set of all vectors with 2 as an eigenvalue. And they've actually written it over here, or we've written it over here. The eigenspace corresponding to lambda is also written as the kernel, and you recall this from first year, of lambda I minus t. Because, just a revision, if lambda I minus t, if it's in the kernel, if v is in the kernel, then this is equal to 0, which means that if you expand this out, lambda v is equal minus t of v is equal to 0, which means that t of v equals lambda v. So something you recall from first year. But basically that's actually how we find all the eigenvectors for a given eigenvalue. And last of all, eigenspaces are T invariant. And that makes sense because if you think about what an eigenspace is, it's basically a set of all vectors such that if you apply T to it, you get something in the same direction as V. And that basically means that if you apply T to it, well, because a subspace is closed on the scalar multiplication, you won't get any new vectors. You'll just get the same kind of thing multiplied by that same value. And that's property number 3. The last two properties that we need to know, so basically what this is saying is that for two distinct eigenvalues, so lambda and mu, they're two different eigenvalues of t, so they're not equal, then the intersection of their eigenspaces is equal to 0. Right, and that kind of makes sense because you can't really be an eigenvalue of two different eigenvalues, right? You can't be an eigenvector of two different eigenvalues, right? If you're in the intersection, then somehow you've managed to achieve two different properties, right? T of v equals lambda 1 v, and T of v equals mu v. And if those are both true, then, well, if you solve for this, you get lambda minus u times v equals 0. Which means that because these are not equal, this can't be equal to 0, that just means that v has to be equal to 0, right? So it doesn't really make sense for something to have two different eigenvalues, and in fact, because 0 is not an eigenvector, it's not defined as an eigenvector, this basically means that you can't be an eigenvector of two different eigenvalues. And last of all, this is from first year. A matrix A is called diagonalizable. And basically what that means is there exists an invertible matrix such that we can express P inverse AP equals D for D a diagonal matrix. And if you recall from first year, this only is true, this only is possible if there are n linearly independent eigenvectors associated with it. And why is this? Let's just draw this out. And we'll go through this algorithm later, but we'll just go through it really briefly because the algorithm for diagonalization, there'll be an example of this later. But basically, if you've got a bunch of eigenvalues with certain eigenvectors, well, the formula for this is D is equal to the diagonal matrix formed from the eigenvalues, and then P, which is the invertible matrix, is just equal to V1 down to Vn. Right, so because the algorithm is like this, all you have to do is just form the eigenvalues and the eigenvectors. It means that it's only going to be diagonalizable if you have these n linearly independent eigenvectors to begin with, because if not, then you'll be stuck on the first step of constructing P. Right, and just recall the method for diagonalization, which we'll talk about later. We have either D equals P inverse AP, or we have A equals P, D, P inverse, right? Hopefully you recall that from first year, but just recall which one comes first. So if you're expressing a diagonal matrix in terms of A, then P inverse has to come first. And if you're expressing A in terms of the diagonal matrix, P has to come first. Okay, so hopefully that we recall that from first year, but that's our basic introduction to diagonalization. Okay, so multiplicities, this is some new content. So, well, this isn't new content because we've done this before, but the characteristic polynomial, which is the polynomial obtained by solving this, because recall that determinant of this is equal to 0 implies that there are non-trivial solutions, which implies that the kernel of A minus lambda I is non-trivial. And that actually implies that there are some eigenvectors with eigenvalue lambda, right? This is all first year content, so we're going through it pretty quickly. But this characteristic polynomial, it'll be a degree n polynomial. Right, so if A is an n by n matrix, this will be a degree n polynomial, and then if you solve it, you get your eigenvalues. And this leads to two definitions. So the algebraic multiplicity, and you can recall it by the word algebraic because algebraic is talking about polynomials. It's the multiplicity of the root for the characteristic equation. So let's say if you've got like the characteristic equation is equal to t cubed, right? How many roots does that have? That has 0 as a root 3 times. So that means that 0 will be a root 3 times, which means that 0 has an algebraic multiplicity of 3, right? That's a really simple way of counting how many of each eigenvalue we have, right? And this will always sum up. The algebraic multiplicities will always sum up to n. We'll talk about that later. The geometric multiplicity is the dimension of the eigenspace associated with lambda, right? Because if you recall, we were solving for the kernel of A minus lambda I. And we always know we're going to get at least one eigenvector out of this if lambda is an eigenvalue. But we could very well get multiple. So we could get that the kernel of this is a span of multiple vectors. And so another way of counting how many of each eigenvalue we have is by counting these independent eigenvectors. So we get the dimension of this kernel, or the dimension of the eigenspace, is the geometric multiplicity. And you can remember that because like geometric kind of implies that you've got this, you can think of it in terms of vectors, right, which is separate from thinking about it in terms of polynomials. And there's this nice theorem. Some people call it like a geometric arithmetic mean kind of analogy, right? But basically it's just saying that the geometric multiplicity is less than or equal to its algebraic multiplicity. So if you, for example, have like a characteristic polynomial where you have 3 distinct roots, then all 3 of these roots only have algebraic multiplicity 1, which means that the geometric multiplicity has to be less than or equal to 1. But, and this is something that you'll use quite a bit, because we know that the geometric multiplicity has to be greater than or equal to 1, because otherwise, if like, let's say gm equals 0, that basically means the kernel is trivial, which means it shouldn't even be there in the first place. It shouldn't be an eigenvalue. But we know it is an eigenvalue. That means it's always also greater than or equal to 1. So what we're basically saying is that if we do have 3 distinct, if everything has an algebraic multiplicity of 1, then, well, the geometric multiplicities also must be 1. But that's a special case of this theorem. Cool. Yeah, and so this is a property that we have over here. So a matrix is diagonalizable if and only if gm equals am for every eigenvalue. Okay, so why is this? Because the sum of the algebraic multiplicities is equal to the degree of the polynomial, which equals n. So if the gm's are actually tagging along with the am's, and all of them are equal, well then the sum of the geometric multiplicities must be n as well. And that means that, well, what is the sum of the geometric multiplicities? That's actually the total number of eigenvectors. right? Because we're taking all the eigenspaces and we're saying, well, this one has 2 eigenvectors, this one has 4 eigenvectors. Let's add them all up, right? And when you add them all up, you get n, which means that we do actually have n linearly independent eigenvectors. I'll just write this as a proper symbol. But yeah, if we have this property hold, then we've got n linearly independent eigenvectors. Cool. So this is basically a formal way of writing that up. So the sum of the algebraic multiplicities is equal to n. But if all the geometric multiplicities are equal, the sum of their dimensions must be equal to n. And that's precisely what we need for diagonalization. But on the flip side, if any of them is actually less, recall this. If equality does not hold, then actually we need it to be less. So if equality does not hold, then we've got an insufficient number of eigenvectors. So when we actually come to add them up, we don't actually get enough. We don't get enough to fill our diagonalization quota, so we can't have diagonalization. Okay, so we'll do some examples now of eigenvalues and eigenvectors, and because of time, we might just do the first one. Or we might have time for the second one, we'll just speed through it. But basically, they want us to find the eigenvalues and eigenvectors, and also the AMs and GMs. So this is a really useful property that helps us move a lot faster in exams. The sum of the eigenvalues is the trace of the matrix. The trace, if we recall from last time, is the sum of the diagonal elements. That means the sum of the eigenvalues, and we know there must be 2, is equal to 5. And we also know that the product is equal to the determinant. The determinant is equal to 1 times 4 minus 1 times 2, which equals 6. Okay, so the determinant is equal to the product of the eigenvalues. And this is kind of like what we get when we're solving like quadratic equations. We're trying to find 2 numbers that add up to 5, numbers that multiply to create 6, and by inspection we've got 2 and 3. So that's a really nice way to basically speed this up. We've got 2 eigenvalues, 2 and 3. And that means that when we come to evaluate the eigenvalues, here we've got this. When we go to evaluate the eigenvectors, we just take the kernel of A minus 2i and the kernel of A minus 3i. We'll do the first one. This is just the kernel of 1, 2, minus 1, 4, minus this thing. And that's equal to the kernel of, I'll just remove this for now. That's equal to the kernel of minus 1, 2, minus 1, 2. And beautiful, it does cancel out. If it didn't, we'd have a problem. And well, a really nice way to just create the span is you don't need to do that like parameter substituting in thing from first year. You can really just, because you know the dimension is equal to 1, just solve this equation trivially. So this is going to be the span of, just find one example of a vector. So if minus 1 times the first element plus 2 times the second element is equal to 0, or let's just say make this element equal to 1. If you make the second element equal to 1, then you've got minus 1 times the first element plus 2 is equal to 0. So x1 is equal to 2. So 2, 1 is one solution. And because you know it's just dimension 1 from the properties of the matrix, we've got that this is equal to the span 2, 1. You can kind of use that technique whenever you've got anything like this. So yeah, similarly for lambda 2 equals 3, you get the same thing, and you can kind of see you're really just trying to solve for where minus 2 times the first element plus 2 times the second element is equal to 0. So let's just say this is equal to 1. Well, then the natural solution to this one is it's equal to 1, 2. You get a span 1, 1. Cool. Yeah. So in other words, you've got 2 eigenvalues, and that's the right number. And if you recall from our characteristic polynomial, actually we don't have the characteristic polynomial, but we know that we know that the sum of the AMs equals 2, which means that if we've just got two different eigenvalues, then, well, each of them can count exactly once, it can't count more. So the algebraic multiplicity must be 1. And similarly, just from inspection, this is the number of eigenvectors. So for lambda 1 equals 2, we've just got this one. And so the dimension of this, which is 1, is equal to the GM. Same thing over here, dimension of this one is just 1, is equal to the GM. Cool. Yeah, so that's just the kind of techniques we can use for algebraic and geometric multiplicities. Okay, same thing over here. This one is a bit more unfortunate because it requires us to actually do calculations. This one we can just calculate the characteristic polynomial, and you'll find that it's equal to, it's not too hard because you've just got the determinant of this, so 2 minus t, 3 minus t, 3 minus t, 1, 1. And you can actually just calculate that as being equal to, in general, if you've got determinant of some matrix, some square matrix over here, and you have a bunch of zeros, and you have another square matrix down here, then you can actually just say that it's equal to the product of these two matrices. Right, if this is A up here, this is B down here. So realistically, when you see something like this, where you've got like a 0, 0 up there, 0, 0 down there, you can actually express it as 2 minus t times the determinant of this one. And that becomes pretty simple, you just get this over here. So right off the bat, from looking at the algebraic multiplicities, oh yeah, that's a good question actually. So someone's actually asked, it might have been a while back, so I'm not really checking the chat too much. But yeah, that's a good question, because the eigenspace, technically, is not strictly the sum, the set of eigenvectors. Where was it? Might have been a long way back. Wow, I need to check this chat. Yeah, it might have been a long way back. But basically, the eigenspace is not strictly equal to the space of eigenvectors. It actually does include 0, simply because we want it to be a subspace. So it's a good question because 0 is not an eigenvector. But we do still want this to be kernel of that, simply because we want it to be a subspace, because it has space in the title, and it has nicer properties if we consider it to be 0. So yeah, technically it is still going to be the kernel over here. So strictly speaking, it's not equal to the set of eigenvectors of that eigenvalue. It's equal to the subset of eigenvectors of that eigenvalue plus 0 as well. Cool. Yeah, back to this, and just from looking at the polynomial, it shouldn't be too complex. We see we have 2 roots 2, and we've got 1 times 4. Right, so 2 has an algebraic multiplicity of 2, and 4 has an algebraic multiplicity of 1. Cool, and then we just calculate the eigenspaces. It turns out that this one over here actually has 2 Li eigenvectors, linear independent. This one over here just has 1. Cool. 1 Li eigenvector. Yeah, and so realistically, just from looking at it, GM2, GM1. And if you were to be asked whether it's diagonalizable, well, because all the algebraic multiplicities are equal to the geometric ones, yes. Cool. Alrighty. There's a second set of examples on algebraic and geometric multiplicities, so we won't go too much into this, but it's basically we're using information and we're explicitly told not to calculate the characteristic polynomial. Basically we have to use the information. So if 2 and minus 3 are eigenvalues, then, well, what we can actually do is try to work out what the last eigenvalue must be. So let's look at the trace. The trace is equal to 2 plus 8 minus 7, which equals 3. And so realistically, what's the final eigenvalue going to be? Well, the sum has to be equal to 3. So lambda 3 is equal to, it would be 4. What does that mean? We've got 3 different eigenvalues, and we know each of those has to generate its own eigenspace. So I just realized my thing has moved a bit. I'll move the I've moved the thing back in the center. Okay, so what I was saying was we've got 3 different eigenvalues. They all generate their own eigenspace. So all of those must be dimension 1, must be separate eigenspaces. So 3 eigenspaces. And because all of these have AM equals 1, because we can only have 3 in total, that means that GM has to be 1 as well. Because we said before, right, geometric multiplicity must always be greater than or equal to 1, and also it's bounded above by the algebraic multiplicity. So that means that we've got 3 separate eigenvectors. So we don't even need to do any calculations. All we need to do is say, because they wanted us to find the eigenvalues and the algebraic and geometric multiplicities, we're actually already done because we did the trace thing. We've got 2, AM equals 1, GM equals 1. Minus 3, AM equals 1, GM equals 1. And 4, AM equals 1, GM equals 1. Cool. Alrighty. So yeah, that's our first example. I'll just write this out. This is just formalizing everything. The arithmetic multiplicity must be 1. Therefore, geometric multiplicity is also 1. Okay, this was our second example. We wanted to find this one, given that we have these 2 eigenvectors. Okay, so well, we're given the eigenvectors, so what we might do is actually apply d to it to see what we get. Because we want to basically work out the eigenvalues. So d times 101 is equal to, let's write this out, equal to, let's just calculate it, it's going to be 1 plus 2, then it's going to be 2 minus 2, which is 0, then minus 3 plus 6, which is 3, and voila, we get 3 times the original 1. So yes, it is an eigenvector with eigenvalue 3. Okay, that's good. What about the second one? Let's do that one as well. I'll just write it out. 1, 4, 2. 2, 1, minus 2. Minus 3, 4, 6. And then we've got 2 minus 1, 2. And then we've got, let's write this out, 2 minus 4 plus 2, which is 0. Wait, sorry, no. That's 2 minus 4 plus 2 minus 4 plus 4, which is 2. Then we've got 4 minus 1 minus 4, which is minus 1. Then we've got minus 6 minus 4 plus 12, which is 2. Okay, so second thing, this must have eigenvalue 1. And hopefully that means we can do the same thing as what we did before. Because now we can look at the trace and see, is it possible that we've got a third eigenvalue that is different? Let's check that. The trace is equal to 8, okay? Which means the sum of the eigenvalues must also be equal to 8. So 3 plus 1 plus the last eigenvalue that we're trying to find is equal to 8. So lambda 3 is equal to 4. And that means, again, we've got 3 different eigenvalues. And hopefully you can already see that that means that we've got actually linearly independent. We've got 3 linear independent eigenvalues. So, yes, by the same rationale as before, AM GM equals 1 no matter what, which is very, very cool. Okay, so just a few more examples, so a few more conditions. So these things are equivalent. T is diagonalizable, and number 2, there's a basis of V consisting of the eigenvectors of T, which basically just means we've got n linearly independent eigenvectors, right, if it's got dimension n, which is what we've seen before. Next of all, we've got V as the direct sum of the eigenspaces, because if you take the direct sum of the eigenspaces, you're just summing up, you're just basically combining all the linearly independent eigenvectors, so you get, you should get the original matrix, the original space. Lastly, over here, the sum of the geometric multiplicities of distinct eigenvalues, well, what is that equal to? That's equal to the sum of the dimensions of all the eigenspaces, which means you're basically summing up all the different eigenvalues. So yes, you should get the dimension of n. So these all make sense. This example we'll go through as well. So basically this is an example that doesn't actually involve matrices. We've got a bunch of vectors, and all we're really given is where we basically go between vectors when we're transforming them. So for example, we have this basis vi, v1, and we don't actually know what the transformation equals. Like, we're not given that it's equal to like 4, 5, 6 or anything. But all we know is that when you apply v1, if you apply t to v1, oh, I just realized my screen is frozen. Oh, this is really sad. I'll just reshare. Okay. All right, give me one moment while I reshare. Okay. I might go through. Okay. Okay. We didn't miss out on that much. I'll go through number 2. Okay. So I'll just summarize what we did. So I'll just go through it again. Yeah. Basically, what we did was we're given the eigenvectors, and because we're given the eigenvectors, we can apply d to those eigenvectors and find the eigenvalues. We found the eigenvalues. We found 3 and 1, and from there, what we did was we worked out the last eigenvalue using the trace. The last eigenvalue is equal to 4, right? Because we've got 3, we've got 1, we have to add up to 8, so now we've got 4, okay? So again, because they're all different eigenvalues, they must be diagonalizable, because we've got 3 linearly independent eigenvectors. All right, apparently it's too zoomed in now. Right, this, I was about to say it was a free app. It actually wasn't free. The app wasn't free, so I feel like I've been scammed because it was free and now it's not working. That's okay. It's better now. All right, take 3. Okay, to be honest, I'll just wait to see that it's okay. It should be okay. Okay, thank you for pointing that out. Yeah, but basically what we did is we found the eigenvalues by applying the matrix to the eigenvectors. We've got 3, we got 1, and so we figured out the last eigenvalue simply by using the trace. You have to add up to 8, so 3 plus 1 plus an imaginary unknown number equals 8. The last one is equal to 4. Okay, that's a really brief summary of what we did. So now we've got 1, we've got 3, we've got 4, so the sum has to be equal to 8, and they're all different, so diagonalizable. Cool. Okay, so conditions for diagonalizability, I went through this before, but all of these 4 properties are equivalent. So number 1, t is diagonalizable. That's equivalent to there being a basis of v consisting of the eigenvectors of t. And that makes sense because we know that if there's a basis of v, it means we've got eigenvectors summing up to the total dimension of the space. So that means it's diagonalizable. Number 3, v is the direct sum of the eigenspaces of each of the eigenvalues. So that kind of makes sense because direct sum means you're combining different eigenvectors into a certain space. So if you can make up v from summing up the eigenspaces, then what you get is a linearly independent set of eigenvectors that makes up the entire space. And lastly, the sum of geometric multiplicities of distinct eigenvalues, that just means we're summing up the dimensions of each of the eigenspaces. So it means that we're taking all of the eigenspaces, counting how many separate eigenvectors we've got. And yeah, if it makes sense that if we've got the dimension of v, then that means it must be diagonalizable. Okay, so that was fun. Now we can actually see the screen, so hopefully this will make more sense. We've got a basis such that we've got these relations between the vectors in the space, right? T of v1 is equal to this sum over here. T of v2 is equal to this sum over here. T of v3 is equal to this sum over here. Okay, so we don't actually know if they're like vectors in R3 or vectors in R4 or whatever. All we know is this relationship. But that's okay because it's actually true that whether or not T, any given transformation is diagonalizable, whether or not that's true is equivalent to whether or not its matrix with respect to a basis is diagonalizable. Right? So you could have the craziest transformation in the world that applies on like a very bizarre vector space, but all you need to do to find out whether it's diagonalizable is find its matrix with respect to a certain basis. Okay? So in this example, can we find the matrix with respect to this basis? Well, we actually can, because in this case, if we recall from last time, the matrix of T with respect to a basis in both domains is equal to, essentially, you just take each basis vector, you apply T to it, and then you take the coordinate vector with respect to the basis. So Steve went through that last time. But yeah, that's pretty simple to see because we've already been given a lot of information about these basis vectors. So for example, T of V1 is equal to this sum over here. So what's the coordinate vector? Well, it's just going to be 2, 1, 1. Because we needed 2 of the first vector, 1 of the second vector, and 1 of the third vector. So that's going to be the first column. The second column will be 0, 2, 0, and this one will be 0, 1, 1. So that's what we've got over here. So really, all we need to do is find out if this matrix is diagonalizable. Okay? And that's pretty simple. We just calculate the characteristic polynomial. I won't go through this because this is just more exciting stuff. But the eigenvalues are given by 1, 2, 2. That's still not enough to show it's diagonalizable. We still have to find the eigenspaces. So we'll do that. The geometric multiplicity of 1 will be 1 no matter what. We don't have to check this, because of that property that if AM equals 1, GM equals 1. Right? But the issue is, this one is a bit more complicated, because we've got AM2, and realistically, GM could be equal to 1, or it could be equal to 2. So we need to check that. We've got kernel of A minus 2i equals the kernel of this, which is unfortunate because it has a dimension of 1. So, in other words, the sum of the geometric multiplicities is 2, and T cannot be diagonalized. Okay? So if we look back at this question over here, they're really asking us, is there a basis of B such that it can be diagonal? Well, even though we just checked for 1, this property over here tells us that if any given matrix with respect to B, if any given matrix of the transformation with respect to the basis is not diagonalizable, it's never going to happen, right? Because diagonalizable, whether or not something is diagonalizable, is actually kind of an intrinsic property, right? If it's not going to work with one basis, it'll never work with any basis. So to answer this question, no, it'll never work, because it didn't work with this guy over here. It didn't work, therefore it'll never work. Okay. Fun. Right, this is our second last example before we, our last example before we move on to something else. So diagonalize the following matrix. I actually won't go through this too much because we actually know this from first year, right? Characteristic polynomial. Express this like this. Factorize it out. So 3 separate eigenvalues. 3, -1, and also 1. Okay, so all we have to do is just find the kernels, right? I won't go through this actually, but all you have to do is find the 3 different eigenvalues and eigenvectors. So first of all, we've got this. Then we've got this. And lastly, we've got this. This is actually really... okay, so yeah. All we have to do then is, as I said before, the diagonalization is as simple as doing this. Eigenvectors eigenvalues. So in this example, what we've done is we've taken -201, that's the first eigenvalue, and put it next to -1. Okay. Then we do the second eigenvalue, 3, then the third one. Right, and all we have to do is just remember our two equations. So either we've got so we've got one of these two things. In this case, we've chosen to basically say that A is equal to P first. So just remember, if A is the subject, you put P first. If D is the subject, you put P inverse first. Okay, so we'll look at the spectral theorem now. So we won't go too much into this, but basically the spectral theorem tells us some information about normal maps. So a linear transformation is called normal if and only if it commutes with its adjoint. So T composed with its adjoint is equal to T adjoint composed with T. And the matrix is normal if this property holds for that matrix. And the spectral theorem tells us a number of properties that this is not the spectral theorem just yet, but there is a number of properties about normal maps. Right, we won't go into them too much because you can just read them in your own time, but we'll move on to the spectral theorem now. Okay, so for a normal matrix, there are two really important properties. The eigenvectors corresponding to distinct eigenvalues are going to be orthogonal, right? So they're actually orthogonal. So if you take separate eigenspaces, they'll have different eigenvectors that are going to be orthogonal to each other. And that means that there exists a unitary matrix. If you recall, a unitary matrix Q is made up of orthogonal eigenvectors, right? So because the eigenvectors for different eigenvalues are orthogonal, we've got this thing over here where we can construct V1 down to Vn. Okay, and these are going to be orthogonal because we know that a unitary matrix is composed of orthogonal columns. Okay, so that means that it can be diagonalized orthogonally. Okay, so there's a second thing that we can know. We had this following theorem for normal maps, but a subset of normal maps is called self-adjoint matrices. So a symmetric matrix or a Hermitian matrix. So if you recall from last time, if AT equals to A, we've got a symmetric matrix. If A adjoint equals A, you've got a Hermitian matrix. So if that's true, then you get what you've got before because they're a subset of normal maps. So you can diagonalize it orthogonally, but also you get this extra property for free. All the eigenvalues are real, right? And that's really useful for later on. And this one over here, we also know that there are two subsets, another subset of normal maps. So normal matrices, we can have unitary matrices. And we can also have self-adjoint matrices. What is a unitary matrix? It's basically a matrix such that its transpose or its conjugate transpose is equal to its inverse. And if this is true, you get another property for free. All the eigenvalues lie on a unit circle. So you'll get e to the I alpha for some alpha real. Right? And of course, in all three of these cases, because they're all normal, you get these two properties. But it's just if you know a bit extra, if you know the self-adjoint, you get this property for free too. And for this one, you get this property for free as well. Okay, so we don't have too much more to cover, but we have, we'll go through this briefly. But a rotation matrix is a matrix of this form. And essentially, all I'll say is that you can show that this is a rotation by alpha about the origin. So if you apply this to a matrix, apply this to a vector. If you take any vector and you apply this to it, the length won't change, but you'll be rotated by alpha. Okay, and there's this other thing in R3, orthogonal matrices in R3. If Q is an orthogonal matrix, which means its columns are an orthonormal basis for R3, then it's going to be similar to one of these two options. Either it'll be like this, which is essentially a rotation matrix, plus 1 at the top, or it'll be this thing, which is a rotation matrix plus minus 1 at the top. And we'll go through this really briefly. The first one is a rotation about the x-axis by the angle alpha in 3 dimensions. The latter is a reflection along with a rotation. Okay, so we're running short on time, but basically what it means is you've got, in the first case, you just rotate by alpha. In the second one, you rotate by alpha, and then you reflect. You reflect about an axis. Okay, so those are our two types of orthogonal matrices. So R will be similar to one of these matrices. Okay, but the question is, how can we work out like which of these matrices it is, and also how can we work out what alpha is? Well, there are two processes we use to do that. So number one, we use the determinant. Okay, so if the determinant of a matrix, determinant of Q is equal to 1, then what that implies is actually it's going to be similar to number 1. And why is that? Because remember, determinant is a similarity invariant. So if the determinant of Q is equal to 1, then, well, which of these has determinant 1? You can show it's going to be this one. This one is determinant minus 1. So it's kind of like it's detective work, right? You're working out, it can't be this one, it's got to be that one. Right, so again, if its determinant is 1, it's going to be unitarily similar to 1. And if not, the other option is minus 1, it will be unitarily similar to 2. And the other one is, how do you find out alpha? Well, again, the trace is a similarity invariant. So if it's going to be similar to, for example, let's just say, like you've done an example, you've worked out it's similar to 1. Well, it comes down to solving for alpha, because now what you want to do is basically the trace of Q is known. The trace of the matrix you're trying to suss out is known. And if you equate that to being 1 plus 2 cos alpha, and you solve for alpha, you've gotten the angle. Okay? But if you find out that it's similar to 2, then what you do is you say the trace of Q must be equal to the trace of the second matrix. So minus 1 plus 2 cos alpha. And having done that, you can then find out what alpha is. I think my screen froze again. That's okay. I'll just do it again. Just give me one moment. Not sure why this is not working too well. One moment. Okay, that's better. Right, we're back on. Yep, okay. I will go through this, but basically this is all detective work, right? So if it's similar to 1, then you can find out what alpha is by solving this equation. If it's similar to 2, you can find out alpha by solving this equation. Okay, so from then on you can work out two things, if it's a rotation or if it's a reflection, and you can also work out what the angle is about which it's rotated. Right, I'll let you read through this example in your own time because we're running short on time. But basically we do these things, right? First of all, we work out the determinant. This means it's a rotation. Then we solve for, I'll go through this later. Yeah, then we solve for alpha and we get this angle. Okay. Alrighty. Okay, so we have two more things to cover, conics and quadratics. Okay, so conics and quadratics, basically they're equations of this form. There's something like x squared plus y squared plus 3z squared equals 5, right? And in general, if you have a shape that only has x squared, y squared, and z squared terms, it's going to be fairly simple to classify as a shape, okay? But the issue is because essentially we can use this table. If we've got signs that look like this, if they're all positive, we've got an ellipsoid. If you've got a plus plus and a minus, it'll be a hyperboloid of one sheet. And all of this stuff, it's basically a matter of cross-checking with the table. But the issue is when we have terms like xy, yz, and xz, because in that case, things get a bit more complicated. But in that case, it's actually pretty simple. There's a pretty simple algorithm we can use to find out what the shape will look like. Okay, so for questions like these, we actually need to express our curve in the form like this. So again, we've not got the kind of equation that's easy. So we've not got like x squared plus y squared plus z squared equals 1. We've got something like this. And what we want to do is basically express it in this form over here. Okay? And let's just do an example over here. X is going to be like this. And to find a, we basically want to compare the coefficients. We want to compare the coefficients over here. It turns out that the 1, 1 term of this matrix corresponds to x and x. So the x squared term will just be this thing over here. Same thing with the y squared term, we'll just get 3 down here. Same thing with the z squared term, we'll just get that down here. And everything else will just be the similar process. So the 1, 2 term over here corresponds to the xy term. There's no xy term, so it'll be 0. And same thing over here, we've got the 1, 3 term. That'll correspond to xz, because that'll be the first one times the last one. So what we do is basically we split this 4 across the 2 of them. So there'll be a 1, 3 term and a 3, 1 term. And we just replace this with a 2. And then the last one is the yz term, which corresponds to the 2, 3 term. And that'll be split across as well. So we'll get 2, 2. Okay. So we've already done this over here. We've got a symmetric matrix. And it's going to be equal to 5, 0, 2, 0, 3, 2, 2, 2, 4. And then A is symmetric. And the reason why we want A to be symmetric is because symmetric matrices can be diagonalized orthogonally. And the reason why that's important is because we want to express the surface as a rotation of another surface. So essentially, we want to make it diagonalized using a matrix that represents a rotation. And orthogonal matrices represent rotations. Okay, so we're going to speed run the last part because we're running out of time. But basically, we diagonalize A. And once we've diagonalized A, we can do some fancy manipulation, but we'll see what that looks like in a second. Okay, again, this is A, and this is our formula. XTA, x equals 1. Okay, so now we have to diagonalize. We've done this plenty of times, so hopefully it's not too complicated. But what we do now is we have to diagonalize into a form where Q is orthogonal. And hopefully we've seen this kind of thing before. But to diagonalize something where it's orthogonal, we need these vectors to be orthogonal as well. In fact, we need them to be orthonormal. But the thing is, using the spectral theorem, because A is symmetric, these eigenvectors are already going to be orthogonal. So all we need to do is standardize their norms so that they're equal to 1. Okay? So yeah, the great news is the vectors are orthogonal already from the spectral theorem. So scale the vectors to have magnitude 1, and we have this. Okay, so perfect. A equals this thing over here. Okay, so at this point what we do is we basically sub that into our formula. Remember we have xtax equals 1. Well, now what we do is we replace this with xtq d qt x equals 1. Okay, and what we then do is we use the fact that a transpose of a product can be expressed as, basically I'll do it over here. Qtx will keep the same. But this is actually the transpose of reversing the order, the transpose of the individual elements. Right, so in general, whenever you have A, B transpose, you get B transpose, A transpose there. That's what we're using over here. And that means we replace this with a substitution. Xt dx equals 1. Okay, and a consequence of that is once we've gotten this new coordinate system x equals qtx, let's just scroll down for a bit. We've gotten this equation. So remember what d is in this case. D is equal to, should write it out, 1, 0, 0, 0, 4, 0, 0, 0, 7. So if we let this substitution x equals xyz, then what we basically get is, instead of this complicated equation with all of these xz terms, these xy terms, these xz terms, we just get something like this. We get xyz times 100004007 times xyz is equal to 1. Okay, and so once we've done that, essentially what we can work out is that this reduces. Remember when I was breaking down the coefficients before, these diagonal terms corresponded to x squared, to y squared, and z squared. And these off terms corresponded to the things we don't like, so like xz, xy, yz. So essentially by diagonalizing and making this substitution, we've essentially gotten something like what we wanted before. We've gotten x squared, because this one corresponds to the x squared component, plus 4y squared plus 7z squared equals 1. Okay, so essentially what we've done is we've broken this down into a formula that we can actually use. And we can identify this as an ellipsoid because all the signs are positive. So recall that table from before. Right, this table from before where we've got all these squared terms and all that. Right, because we have all these squared terms, we can work out just by comparing the coefficients. It can't be this one, it can't be that one. It has to be plus, 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 ellipsoid. Okay, so in other words, if we let x equal qtx, then we get an ellipsoid. Right, and that means we can identify the shape. Okay, but we're not actually done, because remember, we're not using big X, we're actually using little x. So at this point, we start using the relationship between the two surfaces. So remember, in the x domain, our shape is actually just equal to x squared plus 4y squared plus 7z squared is equal to 1. But we're not in the x domain. We're not that divorced from reality. We are still working with the small x's, small y's, and small z's. So what we've realized is that there's actually a mapping between the two surfaces. So remember, qtx equals x, big X, and also qx equals little x. So to get from the points over here, to get from any point in the x domain to a point in the little x domain, you want to multiply by q. So for example, like a point that's of note over here is, let's just say we've got the x-axis. So in an ellipsoid, you have three axes. The x-axis, which is the 1, 0, 0 direction. You've got the y-axis, which is the 0, 1, 0 direction. And you've got the z-axis, which is the 0, 0, 1 direction. That's in this big X domain. So if you want to find the new axes of the new ellipsoid, you need to use this formula. Big X times q equals little x. So really, to find the new axes, you multiply all of this by q. q001, q100, and q010. Okay? So yeah, we've got this over here, a natural bijection. And to get any point of significance on our actual quadratic, the actual surface, we take the corresponding point on the quadratic on the xyz axis and multiply that by q. Cool. And as I said before, the 1, 0, 0 axis, or the x-axis, gets mapped to the q100 axis, and so on. And so the question actually asks us for a number of things. So for the quadratic surface, find the principal axes, the type of surface, and the points, if any, on the curve which are farthest from and closest to the origin. We won't do that last one for now, but the principal axes are just obtained by taking q times 1, 0, 0. So if you recall what q was equal to this. So q times 1, 0, 0 is just equal to the first column. So minus 1 on 3, 2 on 3, 2 on 3. Right? And that means that's the first axis. The second axis is the second one. Third axis is the third one. Okay. Then the point closest to the origin on the xyz plane. Well, let's think about that. In a quadratic, like this thing over here, let's write it out again. We had, where was it? It was x squared plus 4y squared plus 7z squared equals 1. Okay, so if we recall from our theory of ellipses and also conics and quadratics, to get the minimum point, you just need to find the point with the maximum coefficient, so 7z squared, and set everything else equal to 0. Okay, so 7z squared means that if you want, well, for example, if you set everything over here to be equal to 0, you'll get 7z squared equals 1, which means that you can divide by 7. So the reason why we take the max coefficient is then we get z squared equals 1 on 7, and that's a very small number, right? So if you take the number with the max coefficient, set everything else to 0, you end up getting an equation where the solution is very small, because you have to divide by this massive coefficient. So then z equals 1 on root 7. So that's the point that's closest to the origin. The point closest to the origin on the original plane was 0, 0, root 1 on root 7. So again, q maps from big X to little x. So take this point and multiply it by q. And you end up getting this. Okay, so we don't have to do furthest from the origin, but you can sense it's going to be the same kind of problem, right? So instead of taking the point with the max coefficient, you take the point with the minimum coefficient and set the rest to 0. Okay, setting that to 0, you get x squared equals 1, which actually gets you quite a big solution, x equals 1. So I'll just write this down at the bottom as a footnote. Furthest from the origin, it would be q times 1, 0, 0, which equals, in this case, minus 1 on 3, 2 on 3, 2 on 3. Okay, so that's conics and quadratics. A bit of a footnote, this is the table that might be in your lecture notes. Why is it now that we're using the signs of eigenvalues? Because if we recall, we had before d times qtx times qtx transpose. And these diagonal elements corresponded to the coefficients of x squared, y squared, and z squared. And these are actually the eigenvalues. So what that means is that if, for example, all the eigenvalues have positive sign, we'll end up with a conic where all of these coefficients have positive sign. So this is a generalization of the previous table, right? If we've got some conic with like a lot of annoying terms like xz plus xy equals 5, then we don't have to just look at these terms. And now we find the diagonal matrix. We find the matrix that results in this symmetric thing. So at xt a, sorry, not that, xt a x equals 1. And then we find the eigenvalues of a, and we use this table. Okay, cool. And that's the end of conics and quadratics. So I'll see if we do actually have time to go through singular values. Give me just one moment. I'll see if we do have time to go through this as well. Okay, so we do have time. Just give me a few seconds to get something. Okay. Yep. So because we're online, we're happy to go a bit over time. Feel free to watch it afterwards if you have somewhere to be. Yeah, we'll go through singular values and we'll talk about this. So singular value is a way of decomposing any matrix A, which is n times n. Okay. And so what is a singular value? It's the square root of an eigenvalue of A adjoint A over here. Okay, so if we've got the square root of an eigenvalue of A transpose A, and that gives us a singular values, then we can begin to use our singular value decomposition, right? And this looks like a complicated procedure, but it'll make more sense when we do it. But basically, it's a decomposition the middle term is really important, sigma. It has the same size as A. So if A is m times n, this thing will be m times n as well. Okay. So more important than that is the actual process. So what you do basically is you work out the eigenvalues of A transpose A, and you write them in descending order. Okay, and so you write them in descending order. Basically, you've got lambda 1 down to lambda m. Okay, and you'll actually find that they're all actually greater than or equal to 0. Okay, and so what you do is for each of them, you find the eigenvector of unit length. Okay, so just table that in your mind. You found the eigenvalues of A transpose A, and you found the eigenvectors, and you've standardized them to have unit length. Okay, and then you do this process. So for each of these eigenvectors which have non-zero eigenvalue, you calculate this. You apply the matrix to it, and you divide by the square root of the eigenvalue. Okay, and then what you do is you extend this, because you won't actually get a full basis all the time, because this thing over here, I equals 1, 2, all the way down to q, what this is basically is this tells us the rank of the matrix. The reason why it tells us the rank of this is because it tells us the number of 0 eigenvalues. Right? Because if you have a 0 eigenvalue, you don't do this procedure, then you extend this set of eigenvalues, eigenvectors, to an orthonormal basis of Cm. And you use that Gram-Schmidt process to do that. And then you form u and v from the vectors u and v respectively, and you'll find that this matrix is basically just what you get from putting the singular values, so root lambda 1 down to root lambda q, in diagonal, and then filling up the n by n matrix. Sorry, this should be n. And this should be n. Right, so just fill up all of these eigenvalues, and then fill everything else up with zeros. Okay, it'll make more sense once we do it. But basically, we know sometimes to speed this up, we can work out that A adjoint A and A adjoint have the same non-zero eigenvalues. And why do we actually care? Because let's say A is like an m by n matrix, where we've got a lot of columns but not many rows. Then this one over here, remember that our entire procedure hinges upon A transpose A. This thing over here will be something like this, which means when we multiply the matrices, we multiply this row by this column, and we get this massive matrix over here. And no one likes to see that, right? It's just really annoying, right? So instead, if we have n is far greater than m, then what we do is we reverse it. We do it in the opposite order. So instead we do this. And that way we actually end up with a very small matrix. Okay? And that's a lot easier to calculate the eigenvalues for. Okay? So what this lemma tells us is that if we actually swap it around, right, instead of doing A transpose A, we do A transpose, then you'll get the same non-zero eigenvalues, and then all the remaining eigenvalues will be equal to 0. Okay? So you will get fewer eigenvalues because this thing is smaller. But the idea is you fill in the remainder of the eigenvalues with zeros, and then you get a full set of eigenvalues. Okay. So this example, which we'll go through, we won't go through all the algebra because we've done this stuff already, but find the eigenvalues of A transpose. Well, just calculate it. Hopefully we're all okay with using the trace. The trace is 22. The determinant is 120. By inspection, 12 and 10. Okay. Part 2 is basically asking us to apply the theorem we just learned. So explain why the eigenvalues in part 1 are also eigenvalues of A transpose A, right? It's because of what we just talked about. This property that the non-zero eigenvalues of A transpose are equal to the non-zero eigenvalues of the other way around. So what are the other eigenvalues then? Second part of the question? They'll be 0. Okay, so yes. 12 and 10 are also eigenvalues of this bigger matrix, because what would A transpose A look like? It will look like this. And that'll be a 3 by 3 matrix. So it has 3 eigenvalues. So it can't just have 12 and 10, it also needs 0. Okay, then we've got part 3. And what part 3 is part 3 is all the eigenvectors of A transpose A. It's not too hard. We already know that the eigenvalues are going to be 12, 10, and 0. So we just do the kernel stuff. Okay, so yeah. Okay, so you can read through this in your own time, but then part 4 is actually doing the singular value decomposition. In that case, you normalize the eigenvectors. That's step 1. Right? And once you've normalized, you've got already the columns for V. Right? Because remember, the formula is actually, if you go back up, the formula for our matrix transposition, or our SVD, let's just go back here, is equal to U sigma V transpose. So already we have our columns of V. Cool. And that's step number 1. We've got our columns of V. Then, as I said before, you take all the non-zero eigenvectors, so these two, and you just apply this formula. So 1 on root lambda times AV, okay? And you do that for the first one, you get that. Second one, you do that, okay? Then you can actually conclude that the SVD is equal to just taking these U's, we put these in the matrix. So it will be 1 on root 2, 1 on root 2, and also minus 1 on root 2, and also 1 on root 2. That's going to be U. V will be what we saw before, so from these three things, so from these 3 vectors. And then the sigma thing is actually equal to something of the same size as A. A was 2 by 3. So we know that sigma has to be 2 by 3 as well. And what are the actual values? Well, they're the singular values in descending order. So root 12, root 10. And then the remainder are just going to be 0, 0, 0. Okay? So hopefully that makes a lot of sense, because now all we're doing is just subbing in our vectors U and our vectors V. Okay? And so once we've gotten that, we can conclude that our singular value decomposition is equal to this product. Okay? And that's the end of our first part on SVDs and also eigenvalues, eigenvectors, and determinants. We did a lot of important stuff, so hopefully we found that really useful. Without further ado, I think I'll pass on to Jay, who will talk about Jordan blocks and also solving differential equations. Time for a fun delay as we wait for everything to work.
Okay, I can see myself on the stream now. All right, I think. think everything should be all good now. All right, so thank you, Bruce, for doing the first part of or the first half of this part. For my part, I'll be going through the Jordan form as well as the matrix exponential. Mostly will be focused on the Jordan form, because at the end of the day, the matrix exponential bit is really just an application of the Jordan form, anyways. So yeah, we'll focus most of our time on Jordan forms, and then we'll do a few application questions with the matrix exponential. Okay. All right. So firstly, to start off the Jordan form, let's define some basic terms. So for example, we're going to define the Jordan block. Okay. The Jordan block, as you can see here, is going to be denoted as J, and then the size of the matrix, and then the eigenvalue that this is corresponding to. Okay. So in this case, this would be a K by K matrix. We have lambda, which is the eigenvalue, down the diagonal of the matrix. And then right above each of these lambdas, we will place a 1. Okay. This diagonal here is also sometimes called the super diagonal. Okay. And of course, these lambdas here are just sitting exactly on the diagonal. And this matrix here is called the Jordan block. And as you can see, it's pretty similar to a diagonalized matrix, right? So it's pretty similar to a matrix where you just have lambdas down the diagonals. Only difference being you add a 1 on top of each of those lambdas. Okay. And this is just reiterating what I just said. Okay. So let's have a look at some examples of Jordan blocks. This one here is a Jordan block of size 3 with eigenvalue -4. Okay, so it would be a 3 by 3 matrix with -4 down the diagonal, and then a 1 above each one of those eigenvalues. This one here is a Jordan block of size 4. This isn't, I guess you can call it an eigenvalue or not, but just a value in the middle as being 0. So you can see zeros on the diagonal, and then 1s on the super diagonal. Okay. Next, looking at powers of the Jordan form, I've shown, like I've put on this slide, to the power of n, j1, j2, j3, and j4, and let's see if we can detect what the pattern is. So for j1, it's just lambda n. For j2, it is lambda n on the diagonal, and then n choose 1 lambda n minus 1 on the super diagonal. And for j3, you have lambda n on the diagonal, and then n choose 1 lambda n minus 1 on the super diagonal, and then n choose 2 lambda n minus 2 on the one above that. Okay, and we keep going. Okay, so as we keep going, the same pattern repeats. Now, note that the pattern here essentially is that if you read this matrix row-wise, it's really just the expansion of 1 plus lambda to the power of n. Right, because this expansion would just be, I guess, lambda n plus n choose 1 lambda n minus 1 plus n choose 2 lambda n minus 2 plus n choose 3 lambda n minus 3, and so on, right? So if you read the each of these powers of the Jordan form row-wise, it is simply just the expansion of this binomial expansion, right? So 1 plus lambda power of n, okay? And of course, once you hit this term here, once you hit n choose n lambda to the power of 0, then it will terminate. Okay, that will be the end of the matrix. Okay. Again, this is just reiterating what I just said. And as you can see, dot point 4 is exactly what I said. It's pretty much just the binomial expansion of 1 plus lambda to the power of n row-wise. Okay. Another definition is the direct sum. So you may have learned direct sums elsewhere in this course or in first year. But essentially, we're mainly interested in the direct sum of matrices. Okay. And a direct sum of matrices just ends up being one big matrix where you're kind of like putting together all of the matrices that you're direct summing together, so in this case A1 to AN, along the diagonal. And then you pad out all the extra rows and columns with zeros. Okay. So as an example, the direct sum of the Jordan block J23 and J45. So J23 would look like side, so this would be a 2 by 2 matrix with eigenvalue 3, with a 1 in the super diagonal and 0 everywhere else. And this one here would be a 4 by 4 matrix with diagonals with eigenvalue 5, and then 1s on the super diagonal, and then 0 everywhere else. Okay? And the direct sum between these two matrices will just become this big matrix here, where you have your J23 here and your J45 here. And then the remaining rows and columns you just pad out with zeros. Okay? That should be quite straightforward. And now here's another lemma with direct sums. If we're looking at Jordan blocks, then direct summing a bunch of Jordan blocks and then raising its power to n is the same as raising each individual Jordan block to the power of n and then direct summing it. Okay, so again, the example here would be the direct sum of J23 and J12 raised to the power of n. It's just the same as raising this to the power of n, which is this part, direct sum with raising this to the power of n, which is just this part. And of course, again, pad out the columns and rows with zeros. Okay, so it's pretty much the same as this, except you raise each one of these Jordan blocks to the power of n first before you combine together. Okay, and the last basic definition to go through before we actually talk about Jordan matrices is generalized eigenvectors and eigenspaces. This may have already been briefly covered in Bruce's bit, but just to revise here, a generalized eigenvector corresponding to the eigenvalue lambda is a non-zero vector, v, such that this property here is satisfied. So recall that an eigenvector-eigenvalue pair has this property. Okay, this is generalized because it's generalized to any power k. Right? So as long as you can find some value k here, such that when you apply a minus lambda I k times to the vector v, it will return down or reduce down to the zero vector. Okay. So one example here is we have this matrix C and this vector v. Now it should be pretty useful if you pay particular attention to this example, because we will be reusing this matrix C and this vector v in many of the future examples. Okay. So we want to show that for the matrix C, v is a generalized eigenvector corresponding to the eigenvalue of 5. Okay. So to do this, we essentially want to show that we can find such k such that c minus 5i raised to this power k times by our generalized eigenvector v will give us the zero vector. Okay. And we can do so by direct computation. Right? We can just compute c minus 5i times v over and over and over again and see if it turns into zero vector at some point. And that's exactly what we do here. Okay. Firstly, the c minus 5i vector is this. C minus 5i matrix is this. Recall that c was 9, 7, minus 3, minus 2, 2, 1, 2, 5, 2. Okay. So if you minus 5 off the diagonal, it becomes 4 minus 3 minus 3. Okay. And then we do c minus 5i times v once, and that gives us negative 1, 1, 1. So we're doing this matrix times by the vector v, which is 1 minus 2 minus 3. And that gives us this result. And then we do it again to get to c minus 5i squared, right? So if we do this onto this is the same as saying this, right? So if we apply c minus 5i onto this vector, that's the same as having applied c minus 5i squared to our initial vector v. Okay, and so that's what we do here, right? That saves us time so that we don't have to go ahead and compute what the square of this matrix here is, right? So all we have to do is apply c minus 5i to this vector again. And luckily, that reduces exactly to 0, 0, 0. Okay, and we can quickly see that that is true, right? So if you imagine we take this matrix times by this vector, well, then the first value in the vector will be -4 plus 7 minus 3, which is 0. Second value will be 2 minus 3 plus 1, which is 0 again. And then the last value will be -2 plus 5 minus 3, which is again 0. Okay? All right, so we have confirmed that c minus 5i to some power, in this case 2, times by our initial vector v gives us the 0 vector, and so we conclude that v is part of the generalized eigenspace corresponding to lambda equals to 5. Okay. And so finally, defining what a generalized eigenspace is, it's simply just a set of all vectors where this condition is true. Right. So it's essentially all of the generalized eigenvectors corresponding to your value of lambda. Okay. Another interpretation of it is that it's the union of all of the kernels. Okay. So the kernel of a minus lambda I to the power of 1, to the power of 3, to the power of 2, to the power of 3, to the power of 4. It's the union of all of these kernels together, which makes sense because this is essentially just saying the kernel, right? These v's are in the kernel, okay? All right, we've now covered all of the basics of, the Jordan form. We now actually go ahead and think about and talk about the Jordan matrix, okay? So firstly, what is a Jordan matrix? We've defined what a Jordan block is. We've defined what the direct sum is. A Jordan matrix is just a direct sum of a bunch of Jordan blocks. Okay, so we actually saw an example earlier. For example, this one here would be an example of a Jordan block. Of a Jordan matrix, right? It's just a direct sum of two different Jordan blocks. This here can be considered as being a Jordan matrix. Okay. Now, why is it that we care about these Jordan matrices? Okay, I think it's important to talk about the motivation here as well, like for the sake of the motivation. But it's also important because it gives us, I guess, more insight into what we're trying to do in the future steps. Okay, so in Bruce's a bit, he would have talked about diagonalized matrices a bit, right? And you would have seen that was quite useful, right? If you're able to rewrite our matrix A as P times D times P inverse, where P are filled with the eigenvectors as the column, and D as being filled with the eigenvalues in the diagonal, this matrix would have a bunch of nice properties, right? However, the issue is that not every single n by n matrix A will have a diagonalizable form, right? So what we want to find is the next best thing. What's the next best thing such that given any n by n matrix A, we can always find a form that is as close as to the diagonalizable matrix as possible, okay? And that's where the Jordan matrix comes in. Because as you can see from the previous stuff we went through, the Jordan block itself is already quite similar to a diagonal matrix. And so furthermore, a direct sum of a bunch of these Jordan blocks would also be quite similar to a diagonal matrix, right? And so what we can show, we won't show it here, but you should have maybe seen it in the course itself. We can see that we can always rewrite any n by n matrix A as being some matrix P times by some Jordan matrix J times by P inverse. This is something that we can always attain for any n by n matrix A, okay? And so that's our goal, right? Our goal is to learn how to compute or find this matrix J, because then if we can, we can always rewrite any matrix A as being P, J, P inverse, okay? And as for part 2 of our motivation, I guess, throughout the course, you would have learned something called similarity invariance. This includes stuff like determinants and traces, but you were never exposed to a complete set of similarity invariance, okay? And so one thing that the Jordan form gives us is this complete similarity invariant. So for example, if I can write matrix A as being some matrix P times J times P inverse, and some other matrix B as, let's say, Q, J, P inverse, We firstly say that A is similar to J, and we say B is similar to J, because they both have the same Jordan matrix J. But furthermore, if A is similar to J and B is similar to J, then we can conclude that A is similar to B. Okay? So essentially what this is saying is that for any two given matrices, if we can rewrite it in this form of some matrix times J times that same matrix inverse, then we can conclude that those two matrices are similar to each other because they have the same Jordan form. Okay? All right. And lemma 4 is about uniqueness. And that's just essentially saying that for any matrix A, n by n matrix A, we can always find a Jordan form. And furthermore, it will be unique up to a certain extent. Okay? This certain extent phrase, why is that there? Well, that's because if you recall, the Jordan matrix is just a direct sum of a bunch of Jordan blocks. Right? So for example, I could say it's a direct sum of J2, and let's say J3, -1. But that's the same as me saying J3, -1, direct sum J2. That's what it means by unique up to a certain extent, because we can always rearrange the Jordan blocks however we want. Okay? But the main takeaway is that we can always find a Jordan matrix, and furthermore, it will pretty much be unique up to a certain extent. Okay, let's keep going. So, a theorem that we have about Jordan forms is this here. There's a bunch of stuff to talk about here, but the main takeaways is essentially that the kernel of A minus lambda I will always be a subset of a kernel of a higher power of A minus lambda I, right? Which is basically saying that A minus lambda I squared, that kernel, will already contain the kernel of A minus lambda I. And then if you keep going, let's say up to A minus lambda I to the power of, 5, let's say. This kernel of A minus lambda I to the power of 5 will already contain all of the other previous kernels. Okay? And that makes sense because as you raise the power, the nullity will get bigger and bigger, and so the kernel will just contain more and more and more vectors. But those vectors that it contains will also be contained in the previous ones. Okay? We won't prove these results here. They should have been shown in your course. But yeah, we are just revising them here. Okay? The main takeaway is that these nullities, as you raise the power, must not decrease. And furthermore, the differences in these nullities must not increase. So that's essentially dot point 2 and 3. Okay? So it's saying as you raise the power, you will get different nullities, but these nullities must be non-decreasing. And furthermore, the differences between these nullities at each step must be non-increasing. So let's take a look at some examples here. Okay? So again, we're looking at the matrix C. If you go ahead and find its characteristic polynomial, you will get this, which means that it has eigenvalue of 3 and eigenvalue of 5. Okay? Now, in the next 2 slides, we will consider what, was that right? A, it should be C. We will consider what C minus 3i looks like and what C minus 5i looks like. And as you raise its power up, we will investigate the nullities at each step. Okay? So for example, if you look at C minus 3i, it becomes this. If we reduce, it becomes this. What is its nullity here? Well, the nullity is just the number of non-leading columns. In this case, this is a non-leading column, so its nullity here is 1. Okay? Now we raise to the second power, we get this. You reduce. What's its nullity now? Its non-leading column is still this last one here, so its nullity is still 1. And finally, to the third power, it becomes this. And again, its non-leading column is only this one, and so its nullity is still 1. Okay? Of course, you can keep going to power 4, power 5, and so on. But notice the pattern here is that we have 1, 1, 1. This does indeed satisfy our condition that the nullities are non-decreasing, right? So it's not going from 1 to 0 at any point in time. It's always 1, 1, 1. And furthermore, the differences in these nullities are non-increasing. So 1 minus 1 is 0 here. And 1 minus 1 is 0 here again. Right? So these differences in nullities are not increasing. It's staying at 0 in this case. Let's look at lambda equals to 5. C minus 5i is this matrix here. Very reduced becomes this. Its non-leading column is this. So it has a nullity of 1. Okay? We square it becomes this. We reduce becomes this. And now it has 2 non-leading columns. Okay? So its nullity became 2. And again, we raise to the third power, blah, blah, blah. And we again get 2 non-leading columns. It's nullity of 2. So this time the sequence is 1, 2, 2. This still satisfies our condition, because at each step the nullity is non-decreasing. It went from 1 to 2 to 2. It didn't go, for example, from 1 to 2 to 1, right? This would be not allowed, okay? Because nullities would have increased and then decreased. And furthermore, the differences in nullity are also non-increasing. The difference here is 1. The difference here is 0, okay? So it went from 1 to 0. The differences in nullities are not decreasing. Are not increasing. Okay. So these 2 points just summarize what I just said. Okay. So it does indeed follow the condition that it must be non-decreasing, and furthermore, the differences in nullity must be non-increasing. Okay. Now, additionally, note that these nullities seem to be terminating at some particular value. For example, for the lambda equals 3 case, the sequence was 1, 1, 1. By our gut feeling, we should expect it to continue to be 1 forever. For lambda equals to 5, the sequence was 1, 2, 2. Again, just by guessing or hypothesizing, we can guess that it will continue to stay as 2 forever. Note that is exactly equal to the algebraic multiplicity of each eigenvalue. And this is not a coincidence. This is one of the lemmas that we will see on the next page. Okay. So what do I mean? If we go back to our characteristic polynomial, lambda equals 3 has a AM or algebraic multiplicity of 1, and lambda equals to 5 has an algebraic multiplicity of 2. Yeah. And that's exactly also where the sequence terminates. For lambda equals to 3, it terminates at 1. For lambda equals to 5, it terminates at 2. Okay? And that's exactly this lemma here. The dimension of a generalized eigenspace for a particular value of lambda is exactly equal to the algebraic multiplicity of that value of lambda. Okay? And what this implies is that we only ever have to compute a minus lambda I to the power of k up until its nullity is exactly equal to the algebraic multiplicity of lambda, which is exactly what we did here. Okay? Once the nullity has hit 1, which is equal to the algebraic multiplicity of 3, we actually no longer have to calculate any of this, because we already know it will terminate. Similarly, for lambda equals to 5, we didn't have to actually compute the power of 3, because by the time we got to the power of 2, the nullity was already equal to 2, and this is already equal to the algebraic multiplicity of 5. Okay? So that's essentially what this lemma here is saying. And lemma 6 is just some information about AM and GM that Bruce should have also already covered. It's saying that the GM must lie between 1 and the AM. Okay? And recall that the geometric multiplicity simply means the nullity of A minus lambda I. Okay? Okay? I think we're ready to now have a look at how to compute Jordan matrices. So to compute a Jordan matrix, we make use of Jordan chains. Okay? Again, our goal is to rewrite any n by n matrix A into this form, where P is some matrix times by J, which is a Jordan matrix times by P inverse. Okay, so let's say we have a particular eigenvalue lambda with algebraic multiplicity k. how are we going to form this P? How are we going to form this J? Okay. Our goal is to be able to cook up some vector vk such that as we apply a minus lambda I k times, it will eventually reduce it back down to the zero vector. This is exactly the definition of our generalized eigenvector, right? Because recall, if vk is a generalized eigenvector with multiplicity k, we have that a minus lambda I to the power of k times by vk should give us the zero vector back. And so we're essentially just breaking down this entire expression into a chain process where we apply a minus lambda I, a minus lambda I, a minus lambda I k times. Okay. Now, once we have this chain, we can now form part of P. These vectors v1, v2, blah 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 blah, vk minus 1, vk forms the columns of our matrix P. Now, this is quite similar to diagonalizing matrices, because remember in PDP inverse, these P's here were just formed up by the eigenvectors as the column. In our Jordan form here, these P's are formed by the generalized eigenvectors. Okay, so there's quite a nice similarity there. Okay, and one more thing to know is that it's in the reverse order. So when we're doing the chain, we're computing it starting from vk down to v1. In our P matrix, it will enter the matrix going from v1 up to vk instead. Okay. And furthermore, this will correspond to exactly one Jordan block. Okay. So since it's a multiplicity of k, it will form a Jordan block of size k. And since our eigenvalue is lambda, of course it will be jk lambda. Okay. Now, let's further investigate why this 1 is in italics. I want to make clear here that just by doing this Jordan chain process once doesn't mean we're done. This only forms part of our P and only forms part of our Jordan matrix. It doesn't fully give us this form straight away. Now, why is that? If you recall, even just from our matrix C, it has two different eigenvalues, correct? So just doing this Jordan chain process on one eigenvalue is not conclusive, right? Like we don't know if our matrix A has any other eigenvalues. If it does have any other eigenvalues, we have to repeat this process and then add that to our collection in P and our Jordan matrix. So take, for example, that there's actually another eigenvalue. So another eigenvalue, let's say mu, okay? If there is another eigenvalue mu, let's say with algebraic multiplicity of I, okay? That means we have to go and repeat this entire process. So start, for example, with vi, okay? Go down to vi minus 1, down to blah, 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 down to v1, okay? And we have to apply a minus mu I each time, like this, okay? We have to repeat this entire Jordan chain process again. And once we get all our vi's, vi minus 1, all the way down to v1, we then add these vectors to our matrix P. So our matrix P might now look like v1, v2, blah, 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 all the way to vk minus 1, vk. And then we will also have all of these vectors appended to this matrix here. Okay? And then furthermore, our Jordan matrix, now we know, is made up of this Jordan block, direct sum with this Jordan block, and we're still not done yet. There may be other eigenvalues that we don't know of. Okay? And furthermore, you will see later, for one particular eigenvalue, it doesn't mean that there's only one linearly independent Jordan chain. There may be other linearly independent Jordan chains as well. Okay? So what I'm actually saying here is that although this is the process to form our Jordan matrix, doing this process just once is not enough to immediately give us this form, right? We have to take into consideration other possible linearly independent Jordan chains with the same eigenvalue, as well as the Jordan chains of different eigenvalues. Okay. However, typically in exams, the questions will be constructed such that you don't have to do Jordan chain after Jordan chain after Jordan chain. Okay, because at the end of the day, the lecturer just really wants to test you on if you know how to use this method. They don't really care if you do it over and over and over again. Okay. Okay. Now, one last concept I want to go through before doing some examples is the block diagram. I'm not sure if your lecturer would have gone through this with you. It may differ between 2501 2601, and it may also differ year to year. But in the year that I did 2601, my lecturer was John Steele, and he went through this useful trick or concept called the block diagram. Okay, so firstly, what is a block diagram, and what does it convey? The main things that it conveys is the nullities at each step, and by each step I mean each power of a minus lambda I to the power of k. Okay. The second main thing that it conveys is the Jordan chains that can be formed. And lastly, it will give us the overall structure of the contribution of a particular eigenvalue lambda I to the entire Jordan matrix. Okay. Now let's visualize what that means. Suppose we have a generalized eigenspace corresponding to eigenvalue lambda with nullities of 5, 8, 11, 12. The way we're going to draw the block diagram is to take the nullity at each step and add it as if it's like a staircase. Okay. So on the base level, we have a nullity of 5. So that'll be 5 blocks at the base. Okay. Now the next level has a nullity of 8. That's only 3 more in comparison to our first level. So we add 3 blocks on top. Then our next level has 11 as its nullity. That's again only 3 times, 3 more than 8. So we add 3 onto the next level. And then finally, our last level has a nullity of 12, which is only 1 more than our previous level. So we only add 1 block. Notice that this satisfies our condition of nullities. At every single step, the nullities are increasing, but the amount they're increasing by is non-decreasing. That's why it forms this sort of like staircase sort of pattern. Okay. Now, this block diagram obviously then conveys nullities, because if you read the diagram horizontally, that will tell us nullities. For example, this will tell us that a minus lambda I has a nullity of 5. And then at this level, this will tell us that a minus lambda I squared has a nullity of 5 because of the previous level, plus the 3 on this level. So it equals to 8. And this level will have a minus lambda I cubed has a nullity of 8 from the previous level plus another 3. Right? And as you can see, this exactly matches the information provided. Okay? So that's the first one. The next one is it tells you what Jordan chains can be formed. Okay? We won't go through the reasoning here, so just take it on faith. But essentially, if you read the diagram vertically, that tells us what Jordan chains can be formed. So it tells us that a Jordan chain of size 4 can be formed, a Jordan chain of size 3 can be formed, of size 3 can be formed, of size 1 can be formed, and of size 1 can be formed. So we can ultimately write the Jordan matrix here as being a direct sum of a size 4 Jordan block corresponding to eigenvalue lambda plus size 3 plus size 3 plus size 1 plus size 1. Okay? And yeah, and so we can form all of these linearly independent Jordan chains just by looking at our block diagram. Okay? We know that these ones must be able to be formed. Okay? And that also covers our last dot point here of saying that the overall structure of our Jordan matrix can also be conveyed by the block diagram. Now, some extra facts is that Recall, the geometric multiplicity is just the nullity of A minus lambda I, which essentially means that this bottom row here actually tells us what our GM is, right? There is 5 blocks here, so our geometric multiplicity for eigenvalue lambda must just be 5. Okay, and furthermore, if you sum up all of the blocks, this will tell you the algebraic multiplicity of your eigenvalue lambda. Okay, so there's 2 extra things you can get out of this. Firstly, sum of all blocks equals to the algebraic multiplicity of lambda I. And fifthly, number of blocks on the base, so the bottom row, equals to the geometric multiplicity. Okay, so the number of blocks on the bottom row equals to the geometric multiplicity. Okay, now this diagram is very useful in questions, as you will see very soon. Okay, all right. So now let's go through some examples. Example 2. Let A be a matrix with eigenvalue lambda. Explain why this nullity sequence cannot exist. So we have at the first step 5, second step 8, third step 9, fourth step 12, and onwards always 12. Let's just try to construct our block diagram. So in the first level we have 5, which means you will have 1, 2, 3, 4, 5. Next level we have 8, which means that on the next level we will draw 3 blocks because it's 3 more than 5. Next level we have 9, which means we will draw 1 block because 9 is 1 more than 8. But then now we encounter a problem. Because the next level is 12, which is 3 more than 9, which means if we're trying to draw the block diagram, we would be drawing this. But this is not allowed as a block diagram. You can't have this sort of overhang on the block diagram. Okay? So by drawing the block diagram, you should realize that there's actually something wrong. Right? So, like something's not right here. And what's happening here is that this sequence is violating the rule where the differences in nullities must be non-increasing. Right? This is being violated because the difference in nullity here and here is 3. The difference in nullity here and here is 1. But then the difference in nullity between 12 and 9 jumps back up to 3. This is not allowed. Right? We're not allowed to go from 3 to 1 back up to 3. Okay? And thus, this is why this nullity sequence is not possible, because it violates this rule here. Right? And so it's very easy to visualize by drawing our block diagram. Example 3. Let B be a 10 by 10 matrix and let lambda be a scalar, or the eigenvalue in this case. And suppose that it is known we have this nullity sequence so far. We have at step 1, 5, step 2, 8, step 3, 9. Find all the possible Jordan forms of B. Again, we will do this by constructing block diagrams. Okay. Now, firstly, what does it even mean to find all possible Jordan forms? Well, you will notice that since we have a 10 by 10 matrix, this should have a max nullity of 10. Or in other words, if we construct the characteristic polynomial for this matrix, we should end up with a polynomial of degree 10, right? Which means it has a total algebraic multiplicity of 10. But so far we only have 9, which means there's 1 block missing somewhere. Okay, so what I mean by that is, let's draw this out so far. So far you would have 5 blocks on the base, 3 blocks on the next level, 1 block on the level above that, because 8 is 3 more than 5, 9 is more than 8. We only have 9 blocks here, but we're meant to be able to construct 10 blocks in total. Okay, because the max nullity here should be 10. It's a 10 by 10 matrix. And so this question is essentially asking you, where can we find this last final block. Okay. To do this, I will open up a new page because I need a little bit more space to do the working. Let me do that real quick. So let's just add a page to this. Okay, so let's have a look at the first scenario, so case 1. Again, so far we have a block diagram that looks like this. 5 on the base, 3 on the next one, and then 1 in the third level. Okay, and so far we only have a nullity of 9, but we should be able to achieve a nullity of 10. So where can the final block go? This so far is a block diagram corresponding to eigenvalue lambda. If we suppose that we can find this final block in this eigenvalue lambda, what's the only possibility? Okay, we so far already know that at level 1 it has to be 5, at level 2 it must be 8, at level 3 it must be 9. The only possibility is if at level 4, so at level 4, we have a nullity of 10, right? That's our only possibility, okay? Because, again, by the non-decreasing fact of nullities and the non-increasing differences, this is the only possibility. Okay. For example, we can't have this sequence. We can't have 5, 8, 9, 8, 9, 9, 10, because then we have a difference of 3 here, a difference of 1, a difference of 0, a difference of 1. We can't jump from 0 back to 1. So that must mean if we want to get our 10th nullity somewhere, it must come from the 4th level. Or in other words, in our block diagram, it must have one more block up here. Okay. I hope that makes sense to everyone as to why this block diagram here is useful, because it kind of shows us that it must be this case. It must be that this last block comes up here. Okay. It can't be like this. Yeah. Because if it was like this, our block diagram would look something like this. It would look like this, and then like some sort of blank space here, and then another block on top. But obviously that makes no sense, right? Like in this staircase pattern, we can't have this level, this level, this level, nothing, and then a level above, okay? So it can only make sense if we have what I drew earlier, which is this right here. And then now we can again use what we know about the block diagram to very quickly cook up what the Jordan form will look like. So eventually the Jordan matrix must look like a Jordan chain of length 4 for the eigenvalue lambda, direct sum, a Jordan chain of length 2 for eigenvalue lambda, direct sum, a Jordan chain of length 2 for eigenvalue lambda, direct sum, a Jordan chain of length 1 of eigenvalue lambda, and direct sum, a Jordan block of length 1 or of size 1 with eigenvalue lambda. And that's our case 1. Okay. Now let's think about case 2. So case 1, we assume that we can find. Oops, this is too close together. We can find the 10th nullity in the same eigenvalue lambda. In the same, eigenvalue of lambda. So in case 2, let's suppose that we can't achieve the 10th nullity in lambda, right? Which means that there must exist some other eigenvalue, let's call it mu. So suppose there exists another eigenvalue, mu, okay? Which means that our block diagram won't just be one block diagram anymore. It will be composed of this one here, the one that we already know of. Okay? But then plus another one where there's just a single block. Okay? So this is the block diagram corresponding to eigenvalue lambda, and this is the block diagram corresponding to eigenvalue mu. And that is another way we can achieve our 10th nullity, or our 10th block. Right? We will have 9 for this one here and 1 for this one here. And again, we can just read off our block diagram to get our Jordan form. We will have that our Jordan matrix will be the direct sum of a Jordan block of size 3 corresponding to eigenvalue lambda, direct sum a Jordan block of size 2 corresponding to eigenvalue lambda, direct sum a Jordan block of size 2 corresponding to eigenvalue lambda, direct sum a Jordan block of size 1 corresponding to eigenvalue lambda, direct sum a Jordan block of size 1 corresponding to eigenvalue lambda, and then finally a direct sum of Jordan block size 1 corresponding to not eigenvalue lambda, but instead eigenvalue mu. Okay? So these will be our possible cases on achieving our 10th nullity in this question. Right? That's why it says find all possible Jordan forms, because there's actually 2 possible Jordan forms. The case where we can get this last 10th block from the same eigenvalue, another case where we can't get this last 10th block from the same eigenvalue, so it must have belonged to some other eigenvalue that we are letting it be called mu. Okay. I hope these 2 examples make sense and illustrate how useful block diagrams are. So essentially, there's these 5 traits of these 5 traits of block diagrams that you can make use of, and just recall that a block diagram must look like a staircase. Okay, if it doesn't look like a staircase, there must be something wrong with the nullities. So, in other words, you can't have any overhang like this, right? Because this clearly isn't a normal staircase. Right? This is like messed up. Yeah. So if it's like a messed up staircase, then you already know there's something wrong with the nullities. Okay. Okay. Let's move on to example 4. Again, we're recycling the matrix C and the same vector V from before, which is why I said it was important if you just like kind of briefly recall what the matrix C and vector V is, because we'll be using them again here. So in part 1, it says, calculate C minus 5IV and C minus 5I squared V. Again, as you can see in the note, we have actually already done that as example 1. So example 1 was all the way back here, right? We have already computed these 2 things. It's going to be -1, 1, 1, and 0, 0, 0. Okay? Let's go back to our question. Okay? And then question 2, without using any matrix calculation, write down all the eigenvalues of C and their AM and GMs and give reasons. Okay? So from part I, we have figured out that C minus 5IV gave us some vector, I think it was -1, 1, and then C minus 5I squared V gave us a 0 vector, right? Which that already tells us that the algebraic multiplicity of the algebraic multiplicity of eigenvalue 5 must be 2, right? Because the Jordan chain is of length 2. Okay, so we already know that the AM of eigenvalue 5 is 2. Okay. Okay. Now, what about the algebraic multiplicity of the other lambda? Okay. We don't actually even know what the other lambda is at the moment. Well, we can actually already figure that out. Okay. Reason being, recall that in our block diagram, the sum of all of the blocks gives us our total algebraic multiplicity. Correct? So the sum of all these blocks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that will give us the algebraic multiplicity of that eigenvalue, correct? And summing all these blocks together will give us a total algebraic multiplicity, okay? Which means that if we already know that there's a Jordan chain of length 2, then we know that the block diagram for lambda equals to 5 must look like it must have one block on the base, one block on the level above. Okay, because we know that this has a nullity of 1, this has a nullity of 2. Okay, and so for lambda equals to whatever else our other eigenvalue is, it must have a block diagram that looks exactly like just this. It's a single block, right? Because our matrix is 3 by 3. So the total possible algebraic multiplicity should only sum to 3. You can't get any bigger than that, correct? Which means if we already have 2 here from lambda equals to 5, then we must have an algebraic multiplicity for the other lambda equal to 1, because 2 plus 1 is 3. Okay, I hope that makes sense. I'll now actually show you guys the working to this question. So firstly, recall properties regarding trace and determinant. Trace is the same as the sum of the eigenvalues, and determinant is the same as the product of the eigenvalues. So in this case, we can make use of the trace, which is 9 plus 2 plus 2, and that's equal to 13. Now from part 1, record that we know an eigenvalue is 5, and it has an algebraic multiplicity of 2, right? We know that already because it was lambda minus 5 squared, okay? And also because it required 2 of these, right, to the power of 2 to bring it back down to the 0 vector, okay? Which means it must be 5 plus 5 plus some other eigenvalue equals 13, and so the other eigenvalue is actually just 3, okay? And now since this is our only other eigenvalue, and by the reasoning I said above earlier, the algebraic multiplicity of 3 must just be 1. Okay, we know the AM of 5 is already 2, right? Since it's a 3 by 3 matrix, the total AM is 3, so the AM of 3 must be 1, because we need 2 plus 1 to equal to 3. Okay. Now furthermore, using the fact that the GM must be greater or equal to 1 but less than or equal to the AM, we instantly already know that the GM of eigenvalue 3 must be 1, right? Because it's like at the moment it's being bounded above and below by 1. And furthermore, the GM of 5 is also 1. Why must that be the case? Well, earlier I said that the block diagram for eigenvalue 5 must look like this, right? It can't. Okay, so the reason why the GM can't be 2, right, is because if the GM was 2, we would have something that looks like this on the base, and then the 1 for the block above, right? Because recall, GM means the nullity of A minus lambda I. So that's the same as the number of blocks on the base. So if GM was equal to 2, the base must look like this. But we know that we can form a Jordan chain of size 2, so we must also have this. But then that would be a contradiction, right? Because then that would then be a contradiction, because that would have a algebraic. That would then have an AM of 3, right? 1, 2, 3, but the AM is only 2, and the GM must be less than the AM. So this can't be the case. So the only possible block diagram that we can draw is this, and so its GM must also be 1, because on the base there's only 1 block. Okay. So again, we can make use of our block diagram here to deduce our AMs and GMs in combination with this rule here. Okay. Now the third question is, find an invertible matrix P and a Jordan matrix J such that we can rewrite C as PJP inverse. Okay. So the thing is, we actually already have the Jordan chain process for eigenvalue 5, right? Because we did that, again, much earlier in the slides, and that was this here. Okay. We had already done this much earlier. This is example 1. So if you want to refer back to it, this was example 1. We now also have to do the Jordan chain process on eigenvalue 3. Okay, but it's really easy. Reason being, since its AM is only 1, we know that it must just be a Jordan chain of size 1. But a Jordan chain of size 1 must just mean that we have C minus 3i to the power of 1 times some vector, brings us immediately back to the 0 vector. Okay? Or in other words, 3 is simply an eigenvalue, and we just want to find an eigenvector. That's it. Okay? So if we row reduce C minus 3i, we get to here. And then we can obviously just quickly cook up our own eigenvector. And we can see that 102 works, because we multiply by 102 here. Negative 2 times 1 is negative 2, plus negative 1 times 0 is 0, plus 1 times 2 is 2. So negative 2 plus 2 gives us 0. And then the next entry will be 0, 1, 0 times 1, 0, 2. That gives us 0 plus 0 plus 0, which is 0. And then finally, this entire row is 0, so obviously this will be 0. And so we have just cooked up our own eigenvector for eigenvalue 3, and that's it. Okay. So the Jordan chain process for eigenvalue 3 is just one step, and that's because we, I guess, with prior knowledge, already know that the Jordan chain for eigenvalue 3 would only be of length 1. Okay. And so now, just plug in what we have into our P's and our J's. Remember, our P's will be filled up by the column, like the columns of the P will be filled up with the generalized eigenvectors. So for example, this one will come here, this one will come here, and this one will come here. Okay? And then our Jordan matrix will just be filled up by the direct sum of our Jordan blocks. Yeah. So our Jordan block of size 2 with eigenvalue 5, and our Jordan block of size 1 with eigenvalue 3. Okay. Where did we get this from? Remember, our eigenvalue 5 has a chain of length 2, and our eigenvalue 3 has a chain of length 1. That's why this is size 2, and this is size 1. Okay, and that's it. So we have found our PJs and P inverses. Okay. Now example 5 is another I guess, construction of a Jordan matrix. Okay, I will go through 1 and 2. I will leave 3 for you guys to read yourself, because it's really just the exact same process as what we did right here. Okay. Yeah. So let's just go through 1 and 2. So firstly, the question is, you have a matrix A, and we're given that the generalized eigenspace for lambda 2 is a span of 2 linearly independent vectors, and the generalized eigenspace for lambda equals to 3 is a span of just one vector. Okay. So part 1 says, find the Jordan chain for lambda equals to 2, starting with the vector 0, 1, 1. That should be simple enough. It's just saying start with this vector here and just complete the Jordan chain process. In which case, it goes from here to here, here to here. So we know that eigenvalue 2 has a Jordan chain of length 2, and thus we'll have a Jordan block of size 2. Okay. Question 2 is, without any calculation, write down the GM for lambda equals to 2, giving reasons. Okay. So we want to find out what the GM of eigenvalue 2 is. Note that its AM is equal to 2 because it has a Jordan chain length of 2. And recall that our GM must be less than or equal to our AM, which means we can already deduce that our GM must be less than or equal to 2. Okay? But that's not good enough. That's not an actual value. So we can think about it a bit further. All right. Note that we have an eigenspace with a span of 2 and an eigenspace with a span of 1. A is a 3 by 3 matrix. So again, since it's a 3 by 3 matrix, its total AM, so its total algebraic multiplicity, must be equal to 3. All right. Or in other words, in block diagram language, I guess, there must be a total of 3 blocks. Okay? Which means that this one, obviously, since it, for eigenvalue 3, since it's just a span of a single vector, the block diagram for eigenvalue 3 is obviously just a single block. Right? There's no extra levels, there's nothing else on the base, it's just a single span, it's just a single vector. So obviously it will just be one block. Now for eigenspace for lambda equals to 2, we have a span of 2 vectors. Okay? And we know that it's a Jordan chain of length 2. Right? So we have 2 options at the moment. It can look like this, or it can look like this. Right? But since we know that it must have a chain of length 2, based on our working out from part 1, we know that it must take on this form and not this form, right? Because this one would just be 2 Jordan chains of length 1, but we want 1 Jordan chain of length 2. And so obviously just by the block diagram, our geometric multiplicity would just be 1, because that's the number of blocks on the base of our block diagram. Okay? And so we can conclude that our GM equals to 1. Okay? Again, I hope that makes sense and shows you how powerful the block diagram is, right? So we just consider the 2 possibilities, right? If our eigenspace for lambda 2 is a span of 2 vectors, then it must consist of 2 blocks. The only possible diagrams for a 2-block block diagram must be horizontally 2 blocks or vertically 2 blocks. It can't be horizontally 2 blocks because we already know from part 1 that there must be a Jordan chain of length 2. So it must have this structure somewhere in our diagram, so it must be this one. Okay? And once we deduce the block diagram looks like this, we instantly have the GM, because the GM is just a number of blocks on the base. Okay? Okay, so that's question 1 and 2. And then for question 3, again, you just plug in your generalized eigenvectors into your matrix P and form your blocks for the Jordan matrix J. There's one bonus question in this example, and that is find V belonging to eigenspace 2 and W belonging to eigenspace 3 such that V plus W equals to this random vector in I guess C3. Okay. Now we have a theorem here that says that the direct sum of generalized eigenspaces of any matrix A. So if you have a matrix A and you go through this process of finding its Jordan matrix, as part of it, you will find all of its generalized eigenspaces. And it's saying that the direct sum of these generalized eigenspaces will span the entire Cn, right? So C, so like, I guess that's just a vector of size n with its inputs as being complex numbers, okay? So it will span the entirety of Cn, okay? Which essentially means that since we already know what these spans are, we know that eigenspace of 2 is spanned by these 2 vectors, and eigenspace of 3 is spanned by this vector, we can have some scalar times, let me see what the values are again, 132011, let's write this down, 132011 and 142. So these vectors here will span 132, 011, and 142. Will span the entire C3. Okay? Which means if we want a linear combination of this, like of these 3 vectors to equal to 210, we know for sure that that will be possible by this theorem, right? Because the span of the generalized eigenspaces of our matrix A will form any vector we want in C3, okay? And so I'll leave this question as an exercise to any of the viewers. We are essentially just trying to find what A, B, and C are for this equation. Okay. And once you find what A, B, and C are, then you're done. Okay. Now I found a remark on finding Jordan chains. In both examples, we already knew what vector to start with, right? Like for example, here they told you to start with this. For example, in this question, we already knew from part 1 to start with this. Okay, but it's not always that the question tells you what vector to start with. For example, in the 2021 finals, as part of the working out for one of the questions concerning Jordan forms, we were expected to be able to cook up our own initial vector to start with. Okay, hopefully you guys won't have to do this in your exam, but there's always a chance that this will happen. Okay, and I won't go through the entire question here. I will just go through this particular bit that I'm trying to emphasize. Suppose that there's a Jordan chain of length 2 for eigenvalue 2, and we have the following matrix A. Okay, so this is matrix A. How are we going to start the Jordan chain process? To start it, we must first be able to cook up an initial vector to start with, right? So a Jordan chain of length 2 for eigenvalue 2 implies that we have some vector v2. If we apply a minus 2i, we get to v1, and then if we apply a minus 2i again, we get back down to the 0 vector, right? But we don't even know what this v2 is to begin with. So how can we start this process off? So my answer to this is that there is actually no for sure way that you can always generate this vector to start with, right? There's no algorithmic way to do it. The best you can do is to just, I guess, try to figure it out using some tricks, okay? The trick will differ from question to question, but for example, in this one, let's have a look. A minus 2i turns out to be this matrix here. Now, if you notice, we actually have an entire column that is sort of zeros, correct? Which means that a minus 2i times by this vector here will definitely give us a 0 vector, right? Why is that? Because we only have a 1 in the second entry of this vector, which means out of this matrix, it will just exactly extract out the second column. And that's exactly what we want, right? We want to end up with a 0 vector eventually, okay? But that's not good enough, right? This tells us, so this thing we just figured out tells us that a minus 2i times by 0, 1, 0, 0 gives us a 0 vector. But we don't want just this. We want this equals 0. Okay? So essentially, what we know is that we actually want this here to equal to v1, where v1 itself is 0, 1, 0, 0. Okay? So we want to find a v2 such that when we apply a minus 2i to it, or like multiply it by a minus 2i, we get to 0, 1, 0, 0, so that when we then again go to the next step in the chain, and we do it to v1, you will get this. Okay? So essentially, this is the chain. Okay? Okay. So what can we do, right? The main trick here was to realize that we need to end up getting v1 equal to this, such that it extracts out exactly the second column so that we get the 0 vector. But now we need to find a v2 so that a minus 2i v2 gives us v1 in the first place. Okay, so as you can see, it's a little bit of a long-winded trick here, right? Like there is no guarantee way for you to find this v2 every single time. So you have to resort to trying to cook up your own tricks as you go. Okay, so let me open up a new page here and try to figure out what this v2 is. Okay, so recall our matrix a minus 2i looks like 0, 0, 0, 0 here, 0, 0, 0 here, and then 1, 0, 0, and then 1, negative 1 here, and finally 0, 1, 2. Okay, and so what we want is this matrix times by some currently unknown vector, which is our v2, will bring us to 0, 1, 0, 0. Okay? And, okay, yeah, I can see in the comment section here, Asim has given us a working vector of 1, 0, negative 2, 1. And that is indeed the one that we would be cooking up, because that's the simplest one to cook up. Okay, so this should end up being 1, 0, minus 2, 1. Now, let's explain why this works, because it might not be clear straight away why this would work. Okay, so let's say we're trying to cook up this vector here that we don't know yet. Okay, firstly, to get a 0 in the end for this entry, that's the same as saying this row times this vector. Well, this entire column is zeros already, so no matter what is in this column, we will have 0 anyways. Okay, so this is not of much use. Okay, let's consider the next entry. The next entry you want to end up being 1, correct? That is the same as this row times this column. Okay, if we want to force a 1 in here, that means we must have a 1 in here. Oh, sorry, I'll put it in the wrong place. It should be a 1 in the... We should have a 1 in here. Okay, reason being, we want 1 times 1, give us the 1 here, and the rest are zeros. Next, our third entry is also 0. That's the same as this row times this column here. Okay, now how can we get to 0? We have a 1 times 1 so far. That already gives us a 1. So let's just chuck a 1 into the last entry, so that we have 1 times 1 gives us 1, negative 1 times 1 gives us negative 1, so let's say that 1 minus 1 gives us 0 in the end. And then finally, our last entry we want to be 0 as well. That will be this row times this column. And note that 2 times 1 will give us a 2. And we have a 1 here, which means we must chuck a negative 2 here, such that we have 1 times negative 2 is negative 2, 1 times 2 is 2, then we will have negative 2 plus 2 gives us 0 back. And then finally, this second entry here, it can be anything, right? So we can just chuck it as being 0. Okay, and that's how we can, by inspection, cook up this vector v2. Okay, and yeah, once we have cooked up this vector v2, then we can go back and do our Jordan chain process. Okay, so yeah, this was just a small but important remark, right? Don't take it as a given that in the exam they will always tell you what vector to start with, right? You may need to cook up your own, and just know that there's nowhere in the course where they have taught you how to algorithmically get this vector every time. So you may have to resort to, I guess, your own intuition and tricks as you go along the way. And this is an example of one of them. Okay. Okay, hope that makes sense. That pretty much concludes this Jordan chain and Jordan form bit right here. The last... Okay, so asking here's a question. If this A minus 2i was a bit more complicated, so I'm guessing this thing here, would we just have to calculate kernel blah 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 to find a better suitable candidate for V2? Well, yeah, hopefully in the actual exam, if they require you to cook up your own vector, the matrix that you end up with will be sufficiently simple to work with, such that you can resort to these tricks and get it quickly. But yeah, if it was more complicated, you would have to, I guess, keep raising the power and keep calculating the kernels at each step to try to find a suitable candidate. Yeah. But that sort of stuff probably won't pop up in the exam too much, because that will be quite tedious to do. Right. So I would definitely say, in the exam, if they require you to cook up your own vector, try to look for these sort of tricks first, because it is likely that a trick like this will exist. Okay. Have that answered your question? Okay. Let's move on. So the last bit in this Jordan form chapter is the Cayley-Hamilton theorem. It simply says that for any matrix A, that's in this case P by P or N by N or whatever by whatever, as long as it's the same number, then the characteristic polynomial evaluated at the matrix A is always equal to 0. Okay. I'll briefly go through this example here. It's not as important as the stuff we did earlier, but it may pop but it may still pop up in your finals. Okay. So for example, there's a question here that says, basically let V be a vector space, T be a transformation, and we're given that the characteristic polynomial of our T matrix is T cubed minus 5T squared plus 10T minus 6. Okay. Part B says, suppose that we have some vector V. Okay, whoops, this should be bolded to denote vector. We have a vector V in the image of T squared minus 4T plus 6I, where I is the identity map, and it's non-zero. Using the Cayley-Hamilton theorem, prove that the vector V, again, it should be bolded, is an eigenvector of T with eigenvalue 1. I'll just get straight into it. You can't just take the hint given in the question, so you just instantly try and apply Cayley-Hamilton and see what happens. Okay. So firstly, we're trying to show that T of V equals to 1 times V. That's what it means for the vector V to be an eigenvector corresponding to eigenvalue 1. So by the Hamilton theorem, we know that evaluating the characteristic polynomial of T at T will always give us 0 back. Or in other words, T cubed minus 5T squared plus 10T minus 6I equals to 0. Rearranging for T cubed, this implies this. Okay, we just moved all this stuff to the right. Okay. Now, further use the information given in the question. Since V is in the image of T squared minus 4T plus 6I, we know that V must equal to T squared U minus 4TU plus 6U for some vector U. Okay, because if V is in the image, there must be something in the domain that spits out V. Okay. And since we're trying to show this eventually, it wouldn't be a bad idea to then apply T on both sides. Okay. Oops, why did I draw that there? To apply T on both sides. Okay, and that gives us this line here. So T of V equals to T cubed U minus 4T squared U plus 6TU. But now recall that we have this fact from Cayley-Hamilton, which means we can plug that into here. And that's exactly what we do in the next slide. Okay, we replace our T cubed with 5T squared minus 10T plus 6I. And that gives us this. And then by grouping all our terms, 5T squared minus 4T squared gives us T back, T squared back. 10T minus negative 10T plus 6T gives us negative 4T. And then obviously 6U stays as 6U. But now, note where we saw this earlier. This is exactly just this. And so TV equals to V. And that concludes our proof. Okay. Again, this sort of question may or may not come up. It is less important than the Jordan form stuff we did earlier just then. But clearly it has come up in the 2021 paper. So just look out for it if you do see it, right? Okay. That concludes Jordan forms and Jordan matrices. Our very last little bit here is on matrix exponentials. There's not too much that's new. There'll be a few new theorems and lemmas, but then ultimately it will just be questions involving applying what we learned about Jordan forms. Okay. So firstly, we define the exponential of a matrix as just being the Taylor series expansion, but replacing. So like recall, usually when you have e to the power of x, it's going to be 1 plus x squared on 2 factorial plus x cubed on 3 factorial, and so on. Correct? E to the power of ta, we just replace all the x's with at. Okay, that's it. Okay, and the properties of a matrix exponential is that if the matrix A and B commute, then we have the exponent rules. Okay. Furthermore, the inverse of e to the power of A is just e to the power of negative A. Again, you can kind of see that this just follows from exponent rules. And then lastly, the derivative of e to the power of ta just equals to a e to the power of ta or e to the power of taa. Okay? Again, follows normal differentiation rules. Okay. Now, some properties of the matrix exponential is that if you can rewrite A in the form of P times some matrix times P inverse, then the exponential of A is just P, and then apply the exponential to the matrix in the middle, and then P inverse again. Second property is that the direct sum, so if you have A written as a direct sum of a bunch of other matrices, then the exponential of A is just applying the exponential to each of those matrices and then direct summing afterwards. Okay? And lastly, the exponential of t times by a Jordan block of size k with eigenvalue lambda becomes e raised to the eigenvalue times t. And then it will be this big matrix where if you read it row-wise, it's just a Taylor series expansion. Okay? But there's a lot of similarities and analogies to what we did previously. Recall previously when we did the expansion of something like this, it became a matrix where if you read row-wise, it became the binomial expansion. In this case, if you have exponential of t of a Jordan block, row-wise becomes the Taylor series expansion. Okay? Or like, I guess more formally, the Maclaurin series expansion. Okay? This is an example of J52. It will become a 5 by 5 matrix with eigenvalue of 2, which is why we have e to the power of 2t here. And then row-wise, it is just the Maclaurin expansion for the exponential. Okay. So a quick example. Again, the same matrix C. We want to calculate e to the power of tc. We already know p equals to this and j equals to this from our calculations in the previous questions. Okay. Again, very simple. Let's firstly apply the exponential to the matrix J. Since J is a Jordan block, I believe there's actually a t missing here. It should be exponential of tj. Okay. So since J is a Jordan block, we can exactly just apply this lemma here. And so it becomes e to the power of 5t. They didn't factorize it out. So you can rewrite it as e to the power of 5t on the outside. And then on the inside, you just have your Taylor series expansion. Like this. Okay. So we have this here is the Jordan block for oh, sorry, wait, I'm getting confused here. Okay, so there's a reason it was typed like this, because J had two eigenvalues of 5 and 3. Okay, so here is one Jordan block, and here's the other Jordan block. Okay. All right, and so e to the power of c, since c can be rewritten as p times j times p inverse, we can apply the first lemma here. And so it just becomes p on each side of what we calculated just then. Okay? All right. That's a simple example. Next thing is we have the columns technique. So we have a Jordan chain where you have applying a minus lambda I k times. Then we have that the exponential of t times the matrix A times by our generalized eigenvector v1 becomes e lambda t, where lambda is the corresponding eigenvalue. And then in brackets, you essentially have, again, the Maclaurin expansion of the exponential, but at each term in the step, you also have the generalized eigenvector at each step. Okay, that's essentially it, right? It's the same as the Maclaurin expansion, except for at each term in the step, you also multiply it by the generalized eigenvector at each step. Okay. Now, this is where we go into the application of what we learned about Jordan forms as well. we can use what we learned just then about matrix exponentials and Jordan forms to solve, matrix vector differential equations. Okay. So our first theorem here is if we're trying to solve dy and dt equals to the matrix A times the vector y, with the initial condition that at 0 y equals to c, we have the solution y equals to e to the power of at times c. The intuition behind this is, I guess, very similar to what you would have learned in first year. I remember in first year, if you had something like, I don't know, y dash minus some constant, let's say c times y equals to 0, this would be called a homogeneous equation, a homogeneous differential equation, and we would typically guess the answer to be some constant, let's say lambda, times e to the power of t, right? This is lambda, and this should be some arbitrary constant, let's say a, okay? Yeah, same intuition here, except we're working with matrices and vectors, so instead of having scalars a and scalar lambda, we will have matrix A and vector C. Okay, same logic here. Okay, so let's have a look at an example. Again, same matrix C, same vector V. From our calculations many times before already, we know that the Jordan chain for lambda equals to 5 is this. And we want to solve this homogeneous differential equation with this initial condition. Okay, so recall by our previous theorem, the answer should just exactly be e to the power of t times the matrix times the initial vector. So e to the power of t times c times our initial vector v. Okay, but what is this? This is exactly just this, correct? And so we can apply this theorem directly, and we get our answer instantly. Okay, so just applying our theorem, since this vector here corresponds to eigenvalue 5, we have e to the power of 5t. And then inside the brackets, we will have the first generalized eigenvector here, and then plus t times the second generalized eigenvector here. Yeah. Because recall, again, the Maclaurin expansion looks something like this. So the first term will just be times by 1. The second term will be times by t. Okay? And then it terminates there because there is only 2 generalized eigenvectors. Simplify it a bit, and you end up with that. That's it. Okay? Lastly, the last example of the day. What if we have a differential equation where it's not homogeneous? So far we've been dealing with the situation where we have this. Okay. This is called homogeneous because the right-hand side is 0. But what if we have something like this, where we have the right-hand side not depending on y, but it's not 0? This is then called non-homogeneous because our right-hand side is non-zero. Okay? Again, same matrix C. We're now also being told that this vector W is this vector, and it's a given that W is a generalized eigenvector of C. Okay? Well, this time we can't exactly directly apply our theorem here because firstly, it's not homogeneous, and secondly, we're not given an initial condition. So instead, we're still going to make a similar looking guess, but rather than guessing it as being e to the power of tc times the initial vector v, we will just call this vector z. We don't know what this, and we don't know what this is yet. We're trying to find this. Okay. So let's sub in e to the power of tcz into our equation. Applying product rule, you will get this on the left hand side, and then just subbing in e to the power of tcz into y here, you'll get this. And then this term will stay the same. Then notice that on both sides you can cancel this out. And so you're just left with this equals to this, Or in other words, if you left inverse e to the power of tc on both sides, you'll be left with z dash equals to this with the scalars at the front. Okay? But now notice, in the question we were given that w is a generalized eigenvector of C, which means that we can do something about that, right? Because this would exactly fall, this here would exactly fall into this theorem here, where you have the exponential of t to the power of a times by some generalized eigenvector of that matrix A. Okay? And so that's exactly what we do in the next slide. Firstly, we go look at what the Jordan chain for W looks like. And it looks like this. Again, I will skip the details as to why this is a Jordan chain. You guys can try to figure out that yourselves, like when you read the slides later. Okay, but essentially you can form this Jordan chain using W. Then by applying the theorem I just said, you're going to have e to the power 5t because this corresponds to eigenvalue 5. And then within the big brackets, you have the first generalized eigenvector multiplied by 1, the second generalized eigenvector multiplied by t. Right? Again, the Maclaurin series terminates right here. It terminated right here because there is no third generalized eigenvector, there is no fourth generalized eigenvector, and so on. Okay? But now, a small detail is that note that this is e to the power of negative tc, not just e to the power of tc, which means to get our actual answer, we need to make our 5t negative 5t and our plus t minus t. Okay? But now we have a form for e to the power of negative tc, w. Okay? So let's sub that back into this expression here. And that will give us this. Okay? Where this here is e to the power of 5t times by that thing here. So negative 8, 2, 4 plus t, sorry, minus t, because it was negative. Yeah, so minus t. Yeah. So this is just this. And so this will cancel out with this. And so you would just have t times this first vector, and then t times this next component. Okay? And now we're nearly done. We have z dash equals to this. So to integrate on both sides, the t will become t squared on 2. The t squared will become t cubed on 3. And obviously plus some constant vector as the constant of integration. Now note that we can't actually do anything about the c because there were no initial conditions given to us in the question. If there was an initial condition given to us in the question, then yeah, sure, we can go ahead and sub it in and calculate c, but we can't, okay? Because we're not given any initial condition in this question. And then that's exactly what we say in the next slide here. If we did have an initial condition, then we could go ahead and calculate c, but we don't in this question, so we just let it be, okay? All right, and so then we're nearly done. Reason being, we now know what z is. Our guess for the solution y was e to the power of tcz. So now we just sub z in, so that we get e to the power of tc times the first term in z, e to the power of tc times the second term in z, plus e to the power of tc times our constant vector c. Now, notice that these terms here are quite special, right? And this isn't by coincidence either. Whoa, what did I just do? This isn't by coincidence either, because we actually constructed our solution to be this way. Sorry, my tablet is messing up a little bit. Let me reconnect it. Okay. We had purposely constructed our solution to be like this. And what do I mean? Negative 8, 2, negative 4, and negative 6, 6, 6 are already part of a chain that we calculated earlier. So we already know that negative 8 to negative 4 and negative 6, 6, 6 are indeed generalized eigenvectors of our matrix C, which means that we can again apply this theorem here to immediately get this form. Okay, so let's go back down. So on this next slide, you will see this e to the power of tc -8 to -4 will turn into this by the theorem above, right? Because our eigenvalue is 5, and then this is the first generalized eigenvector plus t times the second generalized eigenvector. And then our e to the power of tc -666 will become this. Again, 5 because that's our eigenvalue, and then just -666. Why does it say yp? This is not a particular solution, right? That's just the general solution, since it also includes homogeneous solution plus exponential value tc times c at the end. I do believe that this is still a particular solution. This here would be yh, right? Because we solved the same thing earlier right here, but with y dash minus cy equals 0. We're now solving it as being y dash minus cy equals to t e to the power of 5tw, right? So like this has now turned into a non-homogeneous differential equation because we have a non-zero right-hand side. But yes, like I understand what you mean by it's not really a particular solution because we don't know what the c is, but there is still a difference between what we're doing here and when we calculated the homogeneous solution here. Does that answer your question? Because from first year you would have learned that whenever you're solving the homogeneous solution, whenever you're solving the homogeneous differential equation, the general solution to that will be the general homogeneous solution, which is denoted by y subscript h. But whenever you begin to solve a non-homogeneous differential equation, your solution will end up being yp, because we're guessing this. Yeah. Like this solution here is already different to what we had in the homogeneous case. But yes, we don't know what c is. I guess we are coming up with a non-unique particular solution, if that makes sense. If we had slightly more information, we could come up with the unique solution. But at the same time, I don't think this really at the moment like includes our yh, right? Our yh look like this. But like you're correct. Like it's not like a unique particular solution because we don't know what c is. If we didn't know what c was, then this would be a unique particular solution. Okay. All right. Anyway, so so it becomes this because of the theorem that we said above. This just becomes -666 because the chain here would just be this, right? If we start off at the vector -666, it would just be a chain of length 1. Not 2, not 3, not 4, just chain of length 1. That's why you only get one vector here. And then, of course, finally, we still leave this as e to the power of tc times c because we don't know what c is. And that concludes our answer to that question. Okay, that was quite a bit over time. So I apologize for that. If there's anyone that I guess left already, they can watch it later as a recording. But thank you all for coming, and it would be great if you guys could spend just 2 or 3 minutes filling out this form here, just to give some feedback about today's revision seminar. But besides that, I hope you guys all got something out of today's seminar, and wish you all the best on your final exams. You're all free to leave now if you want. If there's any more questions you want to ask, you can. And of course, try to fill out this feedback form if you have the time. All right. I'll stay here for about 3 to 5 more minutes in case anyone has any more questions. If not, I will close the stream after that. Thank you for coming. There's a question here. The fundamental matrix phi we saw in the lectures. Let me quickly open up the lecture notes. I didn't do this course this year, so I'm not quite sure if I remember what you mean. Let me see. Are these in notes by John Steele for 2601? Okay. So the note should be the same. So I'll have a look. Fundamental matrix phi. Where is this? Okay, I see what you mean. A square matrix whose columns are independent as functions of t and are solutions of y dash is called a fundamental matrix. It's phi t. Well, yes, like I suppose if it's already in your lecture notes and here I can see it as definition 8.5, I think that's probably the same for you. If John Steele has like defined it already, then yeah, like I wouldn't see why you can't just use a definition that he has defined. Yeah, but yeah, like personally, I've never really used the fundamental matrix. I just always kind of do what was shown in the slides. But if you do wish to use this fundamental matrix method instead, then yeah, you can feel free to do that as well. Yeah, like I don't think you would have to prove from scratch again that phi t equals to the columns filled with e to the power of TAV1, e to the power of TAV2, blah blah blah. if it's already shown in the slides, I can assume that you should already be able to use that in the exam without needing to prove it again. Does that answer your question? Yep, no worries. Bye-bye. Alright, I'll probably close the stream now, so